3 years. And it is a special program that really prepares our students to really engage deeply with a hard problem. Really, the students we have here are the best of the best that we have in the Naval Academy. And I know they've been working really hard over the past. I know that next year's Trident scholars, those of you who are here, have already been getting going. And I want to thank you for being here and for all the hard work that goes into it. And I'm sorry, I really, so this is what I promise you. I promise I'm going to ask every Trident scholar at least one hard question. Some of those I will ask when I come see your talks, and I'm going to try to make some today and tomorrow. And some of those, if I don't get you at the main talk, I will get you at the poster session, so do not worry. With that, please enjoy. All right, thank you very much.
Okay, we're going to start off with our first speaker of the morning, Midshipman Trident. Tenley is from the 21st Company. She's an honors math major from Washington, D.C. Her service assignment was surface warfare. She's a member of the Navy Women's Crew Team. And in the fall, she plans to attend the University of Cambridge to pursue a degree in population health sciences.
Okay. Well, good morning, ladies and gentlemen. Today, I'm going to speak on the research I've been doing this past year with the support of the Trident Scholar Program, specifically on Terrell's conjecture, balanced multiplicities, and expected codimension. I'm going to grab this. All right, before I get into the research, I'm going to pose a question. And forgive me for making it ship-related, but I am entering the surface warfare officer community, so we're going to use ships. Let's say I have 3 ships on the ocean. I want to know if the engines go out and the steering go out, which currents will keep them on the paths that I have up on the board. And specifically, how many of those current systems can I use to generate all the possible current systems that will keep them on their paths? These are called tangent vector fields, and this is the mathematics that underlies the property behind Terrell's conjecture, behind what I did my research on. So before we dive into the mathematics, I just want to put my research objectives up on the board. This is what I set out to do at the beginning of this year. And throughout this presentation, I hope to show you how I've hit every single one of these objectives. And to do that, I will first dive into my objects of studies, the mathematics behind my research. Then I will define Terrell's conjecture, this open problem I've been studying for the past 3 years. Then I will dive into what I have done with the problem, which is work on expected codimension and balanced multiplicity matroids. So what is a matroid? Well, a matroid is essentially just a set of rules. It is mathematically defined by a finite set and a set of independent subsets. But let's look at a picture instead. This is the uniform 2-3 matroid diagram right here. It takes 2 points to define a line. So since we have 3 points on this line, one of them is redundant. There's a dependency between these 3 points. And we're going to call these points atoms. So let's take a look at another ship example to help really drive this idea home. We have a carrier strike group. We have a carrier, cruiser, destroyer. They're dependent on each other in our small world. That is our carrier strike group. An aircraft carrier is nuclear powered, so it doesn't require fuel for propulsion, while a cruiser and destroyer do require fuel and sometimes require oilers to deliver that fuel. So there's a dependency between the destroyer, the cruiser, and the oiler. But because there's also dependency between the carrier, cruiser, and destroyer, there's a dependency between the 4 ships. So up here I have a matroid diagram analogy of 2 carrier strike groups and an oiler dependencies. Before we dive further into matroids, I have to define 2 properties, and that's rank and flats. Rank is the size of a maximally independent subset within a matroid, and flat is maximal with respect to rank. So again, let's look at this U23 matroid. And what U23 stands for is uniform rank 2 3 atoms matroid. And you can see here in the Hasse diagram of the lattice of flats, each level shows you the flat of that rank within the matroid. So if I add any atom to this set that is just 3, its rank will increase, and that is why it's a flat. And the reason we care about this definition is this is how I define matroids in my computations later on in this presentation. So we don't care about any matroids. We care about realizable matroids. And what I mean by that is some matroids are represented by matrices. So we have these atom dependencies, and we want to make sure that the columns of a specific matrix match those atom dependencies. And if we can do that, that matroid is realizable. And the collection of all of these realizations is the realization space of that specific matroid. And we can take these matrices and make lines, make graphs from them. And those graphs are called arrangements. So let's return to this U23 example. Here we have one realization of U23. And as you can see, the first column plus the second column equals the third column. So there's a dependency between those columns, similar to we had in the matroid diagram where we had the first dot followed by the second dot and the third dot all on one line. If we multiply on the left by x, y, we get these 3 equations and we get this graph. This is the arrangement, one of many arrangements of U23. It's also right here. So if I move these lines in any way, this creates the realization space of this particular matroid. It's not until 2 of these overlap that this is no longer part of the realization space of this matroid. And what's particularly interesting about the U23 matroid is that it actually represents ranked choice voting with 3 candidates. In the 1950s, there was a theorem produced called Arrow's impossibility theorem, and it won the Nobel Prize. And essentially, it said that ranked choice voting, following these 4 axioms of fair voting systems, can never produce a fair result. And it was proved through brute force social welfare theory at the time. But in the early 2000s, Naval was able to prove this theorem very slickly using arrangements like these. So each chamber here represents a different ranking of candidates. So the blue chamber is candidate A over candidate C over candidate B. And he also did this with n candidates. But here's an example of 4 candidates. So this is what we call the braid matroid. And I actually have a 3D printout of the arrangement here. So in each chamber is a different ranking of 4 different candidates. And as you can see, just by increasing with 1 candidate, the complexity of our example went up quite a lot. In this bottom image, we have the matroid diagram of this specific matroid. This is a projection of that graph. And here's the line of infinity that represents the z equals 0 plane, so that we're able to project the rest of those lines onto this graph. And the reason I put this up here is that the matroids I'm working with are rank 3. So they will look more similar to this than they would the U23 arrangement. And now I urge you to recall the first slide and the current systems I was speaking on. Well, the derivations of polynomials are all current systems in the ocean. So all possible vector fields we can have in the ocean. And the tangent currents, the currents that keep the ships on the path, that's D of A. Those are the systems that run tangent to our arrangement. And the way we're able to check this mathematically is if we have this defining polynomial that is simply the product of each of our graphs of their hyperplane together, and we plug that into a vector field. If we get a factor of our defining polynomial, then that vector field runs tangent. So let's take a dive into one of the most famous vector fields that exists, and that's the Euler vector field. If I plug in any defining polynomial into that vector field, it will get the factor of itself. And we have that right here. So we know that vector field runs tangent to our graph, to our arrangement. So here I bring back the current systems we had before. And the big question I had was how many of these current systems are needed to generate all the possible current systems that run tangent to the arrangement? So how many vector fields are needed to generate all polynomial tangent vector fields? And the answer for our specific case is there's 2 required. If we needed 3 or 4, it wouldn't be free. So what it means for an arrangement to be free is if the amount of generators is equal to the dimension of the arrangement. So we are able to check this through Saito's criterion. And that's where we take a matrix of each of the vector fields and the determinant of it. And again, if that determinant is a factor of our defining polynomial, then that specific arrangement is free. And the reason we care about what it means for an arrangement to be free is that is actually how we define Terrell's conjecture. So if we have a matroid, and that matroid has two different arrangements, if one of those arrangements is free, the other must also be free. If one of them is not free, the other must also not be free. And that's how we define Terrell's conjecture. In the past 40 years, Terrell's conjecture has been proven for up to 14 hyperplanes in rank 3. So my research has been with 15 hyperplanes in rank 3. And what's particularly difficult about this specific problem is that there are frankly so many matroids with 15 hyperplanes. With 11 hyperplanes in rank 3, we have around 200,000. If we add one more hyperplane, we get to 30 million. There is no data on 13, 14, let alone 15 hyperplanes on how many exist. So a safe estimate is to say there's 10 to the 20 amount of matroids that we have to study to be able to prove this conjecture for 15 hyperplanes. So a big aspect of my research is narrowing this down so that we can only focus on the matroids we need to, and we're actually able to do this computationally. And one of the ways we do this is through expected codimension. And that's a way to approximate the codimensional space of a realization of a matroid. And this formula is great in that it helps us compute the codimension quicker than actually hand computing the codimension. It's an approximation. But the problem with this equation is that recursively defined. So it still takes a long time to compute. So one of the goals of my research was to find a non-recursive function for the specific matroids I want to study. In order to do this, I ran many different examples, and here are just a few. The uniform 2-3 matroid has an expected codimension of 0. And not only it, but any uniform matroid has an expected codimension of 0. Additionally, the braid matroid, the ranked choice voting with 4 candidates, has an expected codimension of 4. But even computing that was computationally expensive. But through computations like that, and many more, we were able to come up with this theorem. And that is the expected codimension of any rank 3 matroid is simply the summation of the size of its rank 2 flats minus 2. And we're able to prove this by finding patterns within the formulas and proving these two lemmas inductively. And with those lemmas and being able to cancel out the terms of our recursive function, we get this theorem that's up on the board. This is much more straightforward, and it's much more efficient, and it will really help us narrow down the possible matroids we want to study. Because we were able to prove this for rank 3, my next question was, well, can we generalize this? Can we do this for rank 4 and rank 5 for future mathematicians to be able to use? And this is the generalized formula we proposed. It worked for a lot of examples, but it wasn't until we added a rank 2 dependency in a rank 4 matroid that we were able to find a counterexample. But this generalization in itself was quite fascinating how many examples it worked for. And I urge future researchers to continue to see the applications of this particular formula. Before I get into the next way I narrow down which matrix to study, I'm going to add another definition to our group of definitions, and that's a multiplicity vector. So let's take my arrangement with 15 hyperplanes and zoom in. I want to know how many different hyperplanes intersect at each intersection point along this specific hyperplane. So we have 5 intersecting here, 5 here, 3 here, 1 here. So the multiplicity vector of that hyperplane is 5, 5, 3, 1. And the reason we care about this is how we define balanced multiplicity matroids. So for my matroids with 15 hyperplanes, balanced multiplicity matroids must have multiplicities that are size 4 to 7, must have an intersection point of at least 3 or higher, and can have no intersection point of greater than 5. And so with these rules, these are the only possible matroids that could act as a counterexample to Terrell's conjecture, because any matrix that does not follow these rules would have arrangements that are automatically free, so it would not be a counterexample. Additionally, if you want a matrix to act as a counterexample, it has to be factorable over the integers of the characteristic polynomial. And again, any matrix that does not do this cannot act as a possible counterexample to Terrell's conjecture, because Terrell's conjecture is already true for that specific matroid. But before we dive into why and how we use those definitions, let's use a very fascinating example. This is the only known arrangement with 15 hyperplanes that's realizable before my research began. And not only is it realizable, it has balanced multiplicities in only 2 of them. So every hyperplane in this arrangement has one of two multiplicities, and that was really fascinating to see, in addition to the fact that it's a balanced multiplicity matroid. Unfortunately, it's not the counterexample to Turows' conjecture, but in itself, it was a very helpful example to study to get a better idea of these definitions. So from the rules I stated, I was able to compute that there are 41 balanced multiplicities. So my next question is, well, which multiplicities are connected to each other? And by that, I mean, can they exist in the same arrangement? So again, let's look at the 5, 5, 3, 1 multiplicity vector. Can it exist in an arrangement with itself? The rule with this is that no hyperplanes can intersect twice. So if I'm trying to create another multiplicity vector, I have to make sure the intersections don't repeat. So let's say I take this red hyperplane. It already has an intersection of 5, so we're good there. But we can only pull 1, 2, 3 other hyperplanes to make the next intersection. So 5, 5, 3, 1 cannot exist in an arrangement with another 5, 5, 3, 1. And using this algorithm, I was able to compute there are 573 unique pairings of balanced multiplicities. And here they are up on the board. Note that the way we write the multiplicities here are in partition format. So 5, 5, 3, 1 is there's 2 5s, 1 3, 1 1. And although this looks very symmetric at first, it's not, and it has very interesting details. For example, you can see here 5, 5, 3, 1 cannot map to itself because it doesn't have a loop. Additionally, it only maps to 7 other multiplicities, while the one right above it, which is 3 with 5 2s and a 1, maps to every single other multiplicity. So each of these multiplicities have a range in what they can map to and what they can connect to. And any balanced multiplicity matroid must fall somewhere along the lines of this graph. It will have a path along this graph. So the next step was actually creating an algorithm to compute all the balanced multiplicity matroids. And the first step to that is that we had to eliminate isomorphisms because of the great number of matroids that exist. And the way we did that is found all the possible flat options for 2 multiplicity vectors. Then we use those flat options and iterate them and use a backtracking algorithm to be able to make sure we hit every single possible algorithm that exists, making sure we hold on to the balanced multiplicity matroids characteristics. And this function includes 15 subfunctions. Once we have that function, we have to make sure we iterate through all 573 balanced multiplicity pairings in order to generate all the balanced multiplicity matroids that exist. So for time purposes, we can't dive into the details of each algorithm, but I'm going to present 2 very shortly. This is the 2 multiplicity to all the possible flat options. And what's important about this algorithm is that it made the other algorithms possible to compute. And by that, I mean, due to how many matroids that exist, if we allowed for all isomorphisms to also exist, we could not compute it due to the vast amount. And this brings us to one of our main algorithms, if not the main algorithm. And this is how I create all the possible matroids for 2 multiplicities. And I use those flat options from the previous algorithm to make this possible. I want to note here that it does say I repeat these 4 loops 40 times, which I know for some computer scientists probably hurts the soul a bit. But those 40 times are needed to make sure we are able to backtrack and make every single possibility. And if we didn't have that algorithm before, it wouldn't be 40 times, it'd be 80 times. And that's why we needed to rid those isomorphisms. So once we create these matroids, we have to check the properties. We have to make sure they're realizable. We have to make sure they're factorable, because that's what a possible counterexample needs. Then we rid those extra bit of isomorphisms, and if we find one that has the flexibility to be a possible counterexample, we use Macaulay 2 to check freeness. So here I present what we've computed so far, and we're able to prove that Turows' conjecture is true for these specific multiplicity pairings. And what really surprised me about this research is just the rarity of realizable matroids with 15 hyperplanes. It's about 1 in every 1,000 to 2,000. And that was far less than we expected. Our expected codimension formula we computed was needed if we've had many realizable matroids and we needed to choose which ones to study. But since we had so few, we didn't need to use that formula yet because we didn't have enough realizable matroids. Additional surprise is that the common realizations were modular. And I'd never seen that before computing these matroids. And that was quite interesting to me. And not only were they modular, but they were rigid. And the rigidity made it that they couldn't be a counterexample to Terrell's conjecture. So with these two patterns I've noticed so far, I can say there's high evidence to show that Terrell's conjecture is true for 15 hyperplanes. We need to finish these computations to be able to prove it for all matroids with 15 hyperplanes, but there's high evidence to say it's true. So here's just one example of a matroid we computed, one of our discoveries. As you can see, our matroid diagram has come leaps and bounds from the one we showed on the first slide. And this one is realizable in F5. It has quite a rigid realization. There's no flexibility to it. And it was quite interesting to see that modular space. Here's another matroid we discovered, which is realizable over F4. It looks to have some more flexibility, but in actuality, it doesn't. And our third matroid I present is also realizable over F4, but the very interesting part of this is that it is actually in addition to a matroid we studied previously, and that's called the Hessian matroid. We looked at the Hessian matroid because it had extreme flexibility, and we wanted to keep that flexibility to be a possible counterexample to Terrell's conjecture. So we actually tried manually finding a way to add 3 different hyperplanes to this matroid without breaking any of the balanced multiplicity rules, and we were unable to do it by hand. But when we used the computers and we found this matroid, not only were we able to add 3 hyperplanes, but we were able to add them without increasing any of the intersection points. So we had 12 lines intersecting, and we were able to add 3 more without creating any more intersection points. And that was extremely surprising to see, and I was amazed. It's my favorite discovery. So here is our connection map that I showed at the beginning. As I said, any balanced multiplicity matroid must fall somewhere along this map. And there can be a variety in how many multiplicities it hits. So in the blue, you can see there's only 3 multiplicities it hits. And in the green, it hits far more, but it doesn't always repeat on itself. So there's a wide variety in what a balanced multiplicity matroid can fall on this map, but it must fall somewhere. So here are my research objectives that are now outcomes. So I was able to compute examples for expected codimension, prove a non-recursive formula for the expected codimension of rank 3 matroids, look at this formula for a generalizable, can it be generalizable? And then I continued these restrictions on matroids for balanced multiplicity matroids, created an algorithm that produces all the balanced multiplicity matroids, and began these computations. And from these computations, I made initial discoveries and were able to prove Terrell's conjecture for specific families of matroids. So I want to thank the Trident Committee for helping me support the research and giving me the time and resources to do so. And I want to thank Professor Wakefield for teaching me about algebraic geometry 3 years ago and convincing me to work on this problem. Thank you. Are there any questions? We did not, because it takes more time in the computer to check factorability. So due to how many we had, it was easier to check realizability and narrow those down and then check which of those are factorable. Yes?
Going back to your rank choice example.
Which one?
The 4 candidates.
Yes.
Each volume corresponds to a outcome?
Yeah, so each chamber corresponds to a way you can rank a candidate.
And is each chamber in that printout have equal volume?
Yes, the printout itself couldn't do it due to the 3D printer, but when you expand it, they will all have infinite volume.
Meaning that each one is
equally likely. Yes?
What was the biggest setback you found on doing?
I would say creating the code, we weren't able to run it at first because of how many existed. We did try doing this to create all the matroids, but it wasn't until we created this algorithm that got rid of those isomorphisms that we were actually able to generate them. Because there's so many that if we did not rid these extra isomorphisms, we couldn't compute all of them. Yes?
This might be a question actually for Max, but I'm trying to find out what motivates this study. Originally, Metroids, at least the way it was introduced, was about sort of generalizing linear algebra, matrix theory, and so forth. And I understand why we want to do linear algebra from all the physics problems and so forth. What is the killer application here? What is the application that Metroid theory is trying to address? Is there something that we can point to?
Well, what's amazing about pure mathematics is you don't know the application until you do it. So my favorite example is number theory, and we did not know the importance of prime numbers until computers came about. So although we don't know the applications of this specific research yet, it doesn't mean there won't be one. And that's the entire reason pure math is a thing, is because you find the applications after the fact, after you make the discoveries. Yes?
What are some examples of future work someone could do off of your project?
Well, one, you could go to 16 hyperplanes. That would be the next logical step. But one of my most interesting works is this generalizable formula. It worked for a lot of examples, and I would be curious to see what uses it has in matroid theory.
Any other questions? Okay, let's thank our speaker one last time. And we have a few minutes before our next speaker, so if you want to help yourself to some coffee or some pastry, please do so.
All right, good morning, everyone. Thank you for joining us today. Here to hopefully tell you a little bit about my research that I've done this year as part of the Trident Scholar program. Specifically, I worked a lot in additive manufacturing of plastic scintillators for radiation detection applications. And let's talk about some plastics. So as a top-level overview of what my project entailed is essentially what I was trying to investigate this year was how to develop a potential resin that could be used for 3D printing made out of polyvinyl toluene, a plastic polymer that is commonly used in radiation detection applications, to see whether we can make radiation detectors in a 3D printer. Now, for some background and motivation behind this project, radiation detection is used in all plethora of fields, ranging from defense and energy to border security and making sure that, and health physics. So in particular, the one that really sort of is pertinent to us as DoD and similar government agencies is looking particularly at, for example, either in defense or military applications, making sure that things like radiological threats aren't presenting a harm to troops in the battlefield, or border security, where we typically screen for what we refer to as special nuclear materials, things like uranium, plutonium, things that could be used in weapons of mass destruction, and making sure those materials aren't being moved illicitly or in non-controlled manner. Now, in particular, the way that we detect radiation is, there's multiple different mechanisms by which we do it. Radiation itself cannot really be measured directly, but the way that we do it is through the effects that radiation can cause in other materials. Now, specifically, I examined a type of radiation detecting material referred to as a scintillator. What scintillators, and particularly plastic scintillators, are materials that give off light when exposed to radiation. So what you can see here in that bottom image, or the bottom right image, is an example of plastic scintillators under a black light. It's a really exaggerated effect under a black light, but you can see that these plastics essentially glow when exposed to radiation. When that light is detected, it can then go into a device we call a photomultiplier tube to essentially amplify that signal into something we can actually measure. So the whole point of my project was to figure out, hey, can we make a material like that, but instead of curing it in more traditional methods, can we 3D print with it? The reason for why 3D printing is interesting to us is because it has a myriad of useful applications that traditional manufacturing techniques don't really give us. So what I specifically looked at is a technique of 3D printing referred to as stereolithography, which relies on using UV and near UV light in order to cure a liquid resin, or selectively cure a liquid resin, into a hard plastic. What you can see on the right is an image of the Formlabs Form 4 3D printer, which uses this technique in order to selectively polymerize the different resins into a myriad of different shapes. Now, the reason why additive manufacturing is so interesting these days is because it provides a lot of manufacturing capability for things that aren't as easy to produce using typical parts. That's, for example, components that have very complex geometries. Maybe you only need one-off parts that don't need like a large molder for a large production run. Or alternatively, it can just be another mechanism that the DoD is specifically looking at to replace existing supply chains, because now instead of having a stockpile of ready-made parts that you need to resupply, the DoD is looking at having 3D printers with deployed units so that they can make their replacement parts on the fly when things break. Now, in particular, the reason why this research is interesting is because polyvinyl toluene is a plastic that hasn't really been explored in these sort of additive manufacturing applications in the past, which is sort of the novelty of the research that I was trying to do, and see whether this plastic could be adapted to some of the commercial 3D printing technologies that we have. A lot of these kind of 3D printers are really expensive to develop, so instead of changing the printer to fit the plastic, we're going to see whether we can adapt the plastic to fit the printer. Now, this work does build off of and was in part inspired by previous projects that started here at USNA to try and do basically the same thing. However, instead of trying to develop a new resin from scratch, what those projects really did is attempted to take the existing plastics used in 3D printing and add radiation-sensitive materials to them. Now, the limitations that they faced were several-fold, but one of the big ones is that these plastics like PLA and PMMA that are currently used in 3D printing by companies like Formlabs don't have any sort of measurable radiation response that's useful to us from a detection standpoint. which means that when they were doping these plastics, they would get maybe somewhere between like 0.1 and 1 weight percent of the total material was actually radiation sensitive. So the bulk material, 99+% of it, from a radiation detection standpoint, was functionally useless to us. That's why the goal of my project was to iterate upon that and hopefully have a base resin that if the base polymer is itself radiation sensitive, the bulk material is actually useful to us from a detection standpoint. We can get better effectiveness. The other thing that they saw is like limited solubility and optical clarity, which is important because we need light to be able to travel through these detectors in order for us to be able to reach it, read it and detect it, which is why when these sort of radiation-sensitive materials aren't very soluble in these commercial use plastics, that poses a limitation to some of these past projects. Now, to begin with, what I needed to do is establish a series of and figure out what materials I actually wanted to work with in order to do the 3D printing with. So the Formlabs 3D printers that I was working with, because that's what we have available upstairs, rely on a 405 nanometer either laser or LED screen as the main light source through which to cure the resin that's in there. So, excuse me. As a result, in order to make the chemistry work, the vinyl toluene on its own won't polymerize without something called a photoinitiator, which is essentially the chemical that is triggered by the light in order to initiate the polymerization reaction. So I needed to find chemicals that are both compatible with vinyl toluene and soluble in it, as well as would be sensitive to that 405 nanometer wavelength that the printer gives off and would actually get activated by it. So essentially, based on literature review and what I found in similar research as well as other applications, were two photoinitiator candidates that were potential contenders for this. The first was 1-hydroxycyclohexyl phenylketone. I'll abbreviate it as 1-TAC-HCPK going forward. And then BAPO, which were like the two main photoinitiators that I found in literature as potential candidates. What I did was performed UV-vis spectroscopy, which is a procedure that's used to generate the absorption spectra of different materials on vinyl toluene itself, as well as these two photoinitiators, to see which of these would be potential good candidates for this kind of research. What you see in orange is the molar absorptivity of BAPO, which, while it's not centered and not highest at that 405 nanometer wavelength, it is pretty substantial. However, the other photoinitiator, the 1-TAC-HCPK, doesn't really contain that peak, which is why it wasn't really used when I started moving on to trying to go into the 3D printer for some of these applications. Most notably, vinyl toluene has a very, very low absorption compared to these photoinitiators, which is actually a really, really good thing because I don't want the bulk material to be absorbing the light from the printer. I just want it going to the photoinitiator, which these results show that this combination of vinyl toluene and BAPO were likely to be a potential good candidates for this work. Now, to begin with, before I actually even got to the 3D printer, I also wanted to test these chemical formulations on a broader scale before I move into the 3D printer themselves. So this entailed doing an experiment where I took about 5 to 10 milliliter samples of vinyl toluene and added different loadings of photoinitiator to them and then cured them under a broad spectrum UV lamp. So I wasn't necessarily focusing in on 405 nanometers yet, but the whole point of this experiment was essentially a proof of concept to see whether or not photopolymerizing these chemicals together was actually viable. So essentially what you saw is I had these vials that, kind of like what you can see at the bottom there, and just put them under a broad spectrum UV lamp for what turned out to be a couple days with photoinitiator loadings between about 0.5 and 10 weight percent with a couple intermediate values. What you can see on the right is one of those samples after it came out, and as you can see, under a black light, it showed the same sort of scintillating effect that we expected out of the commercial reference materials, which was at least a promising first sign as far as the fact that the chemistry wasn't going to affect the scintillating properties of our material. Here is sort of the results and how that polymerization reaction progressed. All of the assessments that you see here are qualitative in nature and was really just a way to gauge how much the different samples had polymerized after different points in time. Now, the main conclusions that you can really see here is that the higher the photoinitiator loading, the faster the samples generally polymerize, which is to be expected because there's more material that's able to absorb that incident light and trigger the reaction. Additionally, the one HCPK did polymerize generally faster than BAPO when I tested it during this experiment. However, based on the results that I showed earlier from the UV-Vis spectroscopy, we didn't really end up pursuing it much further because of the lack of absorption at 405 specifically. Now, here you can sort of see the different samples laid out. On the top, you have on the top row there is the BAPO, second row is the 1HCPK initiated samples. Like I mentioned, the higher the photoinitiator loading, the faster they cured. However, it did also have a drawback because you can see that as the photoinitiator loading got higher, especially at about 5 and 10 weight percent, the samples showed more coloring and less optical clarity and more discoloration, which was at least something that we wanted to be mindful of because going forward, if we saw these effects on a broader scale when 3D printing, that could be a limitation of using high photoinitiator loadings. Now, the bottom set of samples you see is the same vinyl toluene that was initiated with a dopant called PPO, which is a chemical that's typically used with vinyl toluene to enhance its radiation response. This experiment was mostly just to see whether or not that would also affect the ability to photopolymerize with it, as well as how much I could actually dope the chemical with. You can see that by the time I start hitting about 20 to 30 weight percent of the bulk material being PPO, the solubility was getting really limited, and instead of photocuring into like a homogeneous material, you started seeing pockets of this undissolved material sort of suspended in the rest of the plastic. This is mostly just to kind of show how the limited solubility at a certain point can affect the final product when polymerizing these kinds of chemicals. Now, after I'd done these experiments, the next stage was to try and get to a more printer-like environment to see after we know that we can photocure with them, whether photocuring with these chemicals at 405 nanometers is similarly possible. Now, the Formlabs printers, like I mentioned, the Form 4 uses an LED screen to cure essentially an entire layer of resin at the same time by selectively turning on different pixels in that screen. Conversely, the Form 2 and 3, which are older versions of the printer, use a laser to essentially trace the path that was going to be cured. What my initial testing was going to do was actually take the laser out of an old Form 2 printer and use that as a reference to build a test bed through which I could test on a smaller scale some of these samples under a UV light to actually see whether or not they're going to polymerize and what that sort of response is, and get an idea of how fast, how much material I need, and essentially get more data before we actually move to full experiments where I had an entire vat of this material. Unfortunately, the laser became the first of several casualties during this project. I may or may not have fried the laser diode. We didn't get very far with this, but that was the first attempt. Second attempt was essentially moving into the Form 4. But again, before I wanted to move on and fill the entire tray with resin, I wanted to see whether this resin would even work or had some viability when it was being tested, which is why I limited it to relatively small samples of about 5 to 15 milliliters. This stage of the project was really filled with me trying to figure out how to work around the printer, even though it would fight me at every step of the way, without actually breaking it, which was mostly successful. What you can see is that the way that I ran these experiments is the top left image shows an empty tray with these two glass dishes, which would actually contain the resin samples. Once I had these two small resin samples, the rest of the tray would be filled with the gray resin that is used by Formlabs in general. The point of filling the tray surrounding those dishes was because the printer tries to detect whether there's enough resin to keep printing. And if there isn't, it tries to dispense more, and I didn't want my samples getting contaminated, hence the need for also like the dishes to separate the resins I was actually testing from the rest of the testing environment. The other thing I really did is I also had to figure out how to get it to print without a build platform present. What you can see in the right image is that arm at the top is normally where the build platform, where the 3D printing material actually, or the 3D print would actually be built on, and that platform gets lowered into that vat of resin. So the whole point was to make sure that that wouldn't interfere with the samples that I was testing. So when I did this, I then essentially had it print and turn on the entire LED screen for varying durations and essentially print the entire layer at a time over and over and over again. At each step, I would then take samples from inside the dish to test to see how fast that polymerization reaction was progressing. And I managed to test 3 different samples with this technique with different loadings of photo initiator. Essentially, every time I found limited success, I kept bumping the photo initiator loading up to see whether or not it would be more successful. Of those 3 samples, only really one actually cured into something that resembled a hard plastic. And that was the 7.8 weight% BAPO sample. What you can see on the right is the sort of plot of the average molecular weight of the polymer after different numbers of cycles inside of the 3D printer. Overall, that sample was rated for a total of about 40 minutes, which is something on the order of, I think, 100 or 1,000 times longer than would be necessary for conventional or the more proprietary resins used by Formlabs. For reference, I think it's the clear or gray resin, usually takes about 30 to 50 millijoules per centimeter squared to cure into a hard plastic. This took somewhere between 24 and 40 joules per centimeter squared. So we're talking about 3 orders of magnitude higher. Additionally, one of the limitations of this research was, or this specific experiment, was that the final molecular weight I achieved, even though it was like a hard plastic that I was scraping out of the dish, it only achieved a final molecular weight of about 2,400 grams per mole. For reference, when I tested a sample of one of the bulk polymerized samples I talked about earlier from that first experiment, that had an average molecular weight of about 23,700, which is about an order of magnitude higher. So even though I was getting a hard plastic, it wasn't really representative of what we saw when we tried to bulk polymerize this same sample. After this, because of some of the limitations of trying to use this dish, I did want to move on and try and see whether printing with a full vat of resin was actually possible. What I discovered is that the dish actually did affect how well the resin inside of it cured compared to outside of it. So that is a limitation with the previous experiment as far as knowing how much of the energy from the screen was actually reaching the resin. Now for the full taking experiments, instead of using 5 to 15 milliliters, I was usually using somewhere between 4 to 600 milliliters and varying a number of different settings to also try and increase the probability of it printing, mainly heating it to possibly increase the rate of the reaction, as well as making sure that the mixer wasn't interfering and mixing up the resin between cycles. Again, similarly, I tested a similar suite of samples with different weight percents of BAPO, even going as high as 15 weight percent. For reference, a lot of the Formlabs resins, their photo initiator loadings are somewhere between 0.1 and 0.5 weight percent. So we're talking about 2 to 3 orders of magnitude higher on the photo initiator. No real samples polymerized when I tried to run this different suite of experiments, which shows a limitation of some of the work. As a sort of potential alternative, I did also try a different photo initiator that I didn't mention earlier, ferrocene. Admittedly, that was really only tested because at the time I was doing these experiments, I wasn't able to buy new materials because of the funding freezes, and I ran out of BAPO. So we worked through it and tried something different. It didn't really work either. This sort of brings me to like the conclusions that I took away from this research, is that the photopolymerization of PVT using the Form 4 does appear to be possible based on some of the like small scale testing that I did. I did get something that resembled a hard plastic, although it wasn't necessarily in the form that it would be when trying to 3D print with it normally. What both the initial experiments showed as well as the full tank experiments is that the amount of energy that is necessary to actually photopolymerize vinyl toluene is actually really substantial, which may make it prohibitive to actually print with in the specific application of the Form 4. However, I do think what my project has opened up is a lot of avenues that I didn't necessarily have time to explore, that luckily there's a follow-on Trident that is hoping to do some of this work next year, and this is some of the techniques that she will be using to possibly get more success when trying to 3D print with vinyl toluene. One of the big ones is trying to pre-polymerize the resin. A lot of the Formlabs resins start more viscous and more polymerized than the materials I was working with. So maybe if it's starting more polymerized to begin with, getting it to a hard plastic at the end is a lot more viable. There's also a lot of different chemical compositions that could be tried, ones that I didn't get to explore. I mostly worked with BAPO and vinyl toluene, but there's plenty of other chemicals such as cross-linkers, dopants, photoinitiators that I didn't test in the printer. Additionally, one of the biggest limitations is I had to find a lot of workarounds to actually work with the Form 4, both to conserve material when funds weren't available to purchase more, as well as to just not to work in some of these more experimental settings that the printer wasn't designed for. However, since then, we've also acquired the Open Materials Mode license, which is specifically meant for working with non-proprietary resins. Again, unfortunately, because of some of the purchasing and administrative issues, it took months to actually acquire that to a point where I wasn't able to explore it. But it does offer avenues where it may offer features that may be useful to 3D print with. As a final note, just like to leave a couple thank yous and acknowledgements, specifically to all of my advisors which are here today, Professor Joyce, Commander Lotta, and Professor Baromi, whose technical support has been tremendously helpful throughout this project. The Behrens family funds the Behrens Scholarship, which was used to fund this research, and tremendously grateful to have the opportunity and that support. I'd also like to thank the other mechanical and nuclear engineering faculty and staff, specifically Commander Slager, whose background in 3D printing and access to the makerspace was really useful. I've also had some support from the ECE department faculty who have been able to provide technical advice, especially back when I was doing some of the laser testing. And then finally, DITRA and INSERC fund a lot of the nuclear-related projects here on the yard, so their support for our work here has also been tremendously useful. And now, if anyone has any questions, more than happy to answer them. So the reason why we did the Form 4 is essentially vinyl toluene starts as a liquid. So the reason why the extrusion printers wouldn't be as useful is because they require having like a plastic filament to feed into it, which we didn't really have with vinyl toluene. Vinyl toluene isn't a plastic that we can as readily melt down and then have it re-solidify. So that was essentially the main reason, is because we were starting with a liquid resin, which is what the Form 4 is designed for.
Are there any other types of liquid resin printers that might use different wavelengths, allowing you to use, let's say, a different thing that you dope the resin with than the backup?
Yeah, that's absolutely a possible avenue. There's plenty of other commercial 3D printers out there. I mostly worked with the Form 4 because it's what we have available here in the makerspace as our main UV curing printers. But there are plenty of other commercial printers out there. Some of them might have access to things like higher power levels that they're able to achieve. Maybe they use different wavelengths. All of that is possible avenues that could be left to explore, and maybe some of those may be more conducive to working with vinyl toluene. That's absolutely a possible avenue for future work. Yes, sir?
Just wondering if you have given any thought to the sensitivity of this topic. Do you feel it can be published in open domain?
I think you mean like whether the work sort of as it stands being publishable? I don't know if the work sort of where it stands right now is in a position to be published. I think the results that I had found during the scope of this year are rather limited in terms of the final results I was able to achieve, but I think that there's a tremendous amount of work left to be done in this field, and I think that it has a lot of potential once it's explored a little bit further.
I think he's asking about classification.
Right. I'm not worried about quality. The quality looks terrific to me. I'm just wondering about the kind of applications you have in mind, especially at the beginning when you mentioned about how radiation is being used to detect wetness and so forth. It seems really sensitive. I'm just curious. Given thoughts to that.
So I haven't necessarily really considered the sensitivity level. I think at this point, just trying to 3D print with these materials is a relatively sort of entry-level research. We're not really at the sort of application level yet where the sort of classification may be required for a lot further research. I think once we start looking into it, and because a lot of, for example, agencies like DTRA are looking into things like 3D printing of radiation detectors as a whole, once we were to move towards more of that application level of what are we actually trying to 3D print with it, what kind of radiation are we detecting with it, that's probably where we would see some of that sensitivity of this material being applied. Yes, ma'am.
Thank you for the presentation. You're knowledgeable about this very well, and you use all the expert level language and all of that. That's all. When you look back, you have spent about more than a year on this project. I don't know if you had studied before you became a Trident. When you look back, what do you think you would change? You know, like it's always easy to be general when the ground is over. What would you change in order to achieve some level of, like your words, better success?
So I think in retrospect, like if I had to look back, there are a number of sort of steps that I took with this project that sort of led me down paths that didn't really yield much results. I mean, for example, even like trying to use the laser and develop that test bed probably took about a month's worth of time between taking apart the printer, getting all the safety and medical certifications for working with a laser, and then ultimately like getting the approval in spaces. So that alone took up time, because at the time that felt like a good avenue to do some of these initial kinetic experiments where I could figure out, okay, how much energy does it actually take when working with a 4 or 5 nanometer source? In retrospect, was that particularly useful? Not really, because I didn't get a whole lot of useful data once the laser was dead. So if I didn't go down that route, maybe I could have gotten to the printer sooner, maybe I could have done some of this work a little bit faster. So, I mean, that's just one example of sort of, I think that's sort of the nature of, exactly, but I think that's also the nature of research, is sometimes we make decisions that.
I was hoping that you would kind of give a killer path to a next student that I think you mentioned, somebody who's coming up. Is, hey, do this, it's gonna work.
Yes.
That's
And I,
what I'm looking for.
yes.
I know that you don't think it will work. I mean, like,
No, of course, and I think that's sort of like a lot of the future work. I think if there's one success that I think this project has done, is it's sort of overcome a lot of the more administrative and preparatory hurdles as far as figuring out whether we can use the 3D printer, how to use it best, what settings do we have access to. So even though I wasn't able to explore and as thoroughly research and test all of those settings, I at least was able to sort of uncover and find what possible alternatives are out there. So I'm really talking with like my successor as far as, here's the things that I know, here's the options that are available to you. And I think that's sort of one of the main successes of this project, is at least laid a lot of the groundwork so that she no longer has to, for example, when I mentioned like trying to bypass all of the different checks with the Form 4, that was all sorts of headaches trying to just get the printer to do the testing I wanted. Now that we have the open materials mode license, that has made a lot of this work redundant, but at the time, I didn't have access to that, but now she does. So it's a lot of options like that where now that I've gone through some of the headaches, gone through some of the struggles, now she doesn't have to, so she can sort of jump straight towards the actual testing of the material.
If there's no other questions, let's thank our speaker one last time. Okay, we have about 5 more minutes before the next speaker. Started.
Two of those three is too many.
We're going to continue on. We've heard a number of great talks already. Just a reminder that we have talks all morning today, and then tomorrow we have talks all day. So if you have time tomorrow to stop by and hear a few talks, it would be great to support these midshipmen. So our next speaker is going to be Midshipman Jeffrey Davis. He's from the 27th Company. He's a mechanical engineering major from Sour Lake, Texas. His service assignment was submarine warfare. In the fall, he's planning to attend Stanford University to pursue a master's degree in mechanical engineering.
Hi everybody, as Professor Schroeder just mentioned, my name is Midshipman Jeffrey Davis. My project is measurement and modeling of optical turbulence through the near maritime atmospheric boundary layer. And I'm being advised by Professor Burkhart and Brownell in the Mechanical and Nuclear Engineering Department and Professor Nelson in the Electrical and Computer Engineering Department. So just to frame the discussion that we're going to have today, the Navy and the Marine Corps are interested in optical systems for a variety of applications, but the applications that are perhaps the closest to being ready for field use are laser weapon systems. And laser weapon systems are useful to the warfighter, to the naval commander, because these weapon systems give the naval commander a cheaper option to combat threats to their ship, to their unit, than perhaps an SM-11, which costs $6 million, $11 million, right? These lasers cost about $13 a shot, so they're much cheaper once they've been developed to attack threats like drones or possibly even ballistic missiles in the future. However, optical systems encounter a variety of obstacles, particularly when propagating in the atmosphere, right? The lowest level of the atmosphere, the atmospheric boundary layer. And one of the most potent issues that they run into is effects from optical turbulence. And optical turbulence is the variation of index of refraction in the atmosphere, and it leads to this non-uniform refraction. So as an example, if you think about a coherent wavefront, which is what a laser is, that has an intensity profile such as the one on the left, as it goes through the atmosphere and different parts of the wavefront refract at different rates, then it comes out on the other side perturbed. And this shows the perturbed intensity profile. It's no longer coherent as it was when it entered the atmosphere, but instead you have this variation in intensity. And that's caused by these turbulent eddies that are throughout the atmosphere. And an eddy is you can think of it as a bubble of air that's really amorphous in shape, but it's easy to think of them as elliptoids as they're depicted here. And all of these eddies have properties independent of the other eddies in the atmosphere. They all have different temperatures, different pressures, different indices of refraction. And the indices of refraction, the difference in indices of refraction causes these differences in the refraction of the different parts of the wavefront. Another effect of these turbulent eddies in the atmosphere is that a beam of light that goes through the atmosphere would enter the atmosphere normal to the target that it's trying to hit. However, when it comes out the other side, as depicted by these arrows, it comes out at an angle that is no longer normal to the target. This is known as the angle of arrival. And both this variation in intensity and the angle of arrival can be used to measure optical turbulence in the atmosphere. The variation in the intensity is known as scintillation. And scintillation effects, there's a few different scintillation effects, but the two that I'll focus on here are beam spread, which is depicted by the top left-hand corner, and beam wander, which is depicted by this video here that I took in a lab about a year ago now. And in beam spread, the beam spreads beyond the diffraction limit, which is the amount of spread that you would expect a laser beam to have in a vacuum. And this decreases the irradiance on target, which increases the amount of dwell time that we need to have on target in order to achieve whatever mission it is, whether it's burning a hole through a drone or it's communicating with an aircraft. And likewise, the beam wander, the wandering of the centroid, decreases the average irradiance on the target. If the target is this white circle, then the centroid goes in and outside of that circle, and then we lose irradiance over time. Depicted in the bottom right-hand corner here is the angle of arrival effect. So you see this target board. One picture is just taken from a couple feet away, and one picture is taken from downrange. And you can see that the features of this target board become less clear and less sharp after going through the atmosphere, after experiencing significant optical turbulence. And we can use each of these to measure optical turbulence. But before we talk about the measurement, I want to go over what causes optical turbulence in the atmosphere. And specifically, in the lowest level of the atmospheric boundary layer, optical turbulence is driven mainly by buoyancy effects. So when you have a water surface that has radiant heat from the sun on the surface, it causes the surface to heat, right? And then that hot water then has heat transfer to the air that is lower temperature immediately above it. And once that happens, you have high temperature air situated below low temperature air. And of course, the high temperature air wants to rise and the low temperature air wants to drop. And this causes this mixing effect. And this mixing is how eddy formation happens primarily in the atmosphere. There's other things, of course, like wind and water currents that might have an effect, but buoyancy effects are the greatest effect of optical turbulence, of turbulence formation in the atmosphere. And these effects are most significant in the lowest level of the atmosphere, like I said. And it's in this lowest level of the atmosphere that we care the most about turbulence, because this is the region in the atmosphere where a naval commander is going to be using their optical systems. They're not going to, typically, these threats that we're encountering, the drones, the missiles coming in, are going to be on slant paths within the atmospheric boundary layer. They're going to be on these paths that are neither completely horizontal nor completely vertical. And so we need to understand how slant paths behave in this environment. So in order to understand this, we took measurements of a slant path, right? We used the delta WX, which is depicted there, and it's sitting on the deck of the sailing center over right next to Santee Basin. And we observed the top of the Greenberry Point Tower, which is the tallest structure that we have to observe a slant path near the Naval Academy. We also want to understand, like I talked about before, the interaction between turbulence and the meteorological parameters that are available for us to measure. And so to measure our meteorological parameters, we use the NOAA station and the Oceanography Department's weather tower that are located right next to Santee Basin to collect our meteorological parameters. So this diagram here shows how the delta WX is making a slant profile up to the top of the Greenberry Point Tower. And you'll notice that there's 10 bins, as I'll refer to them, resolved along this path. So because the delta WX is able to resolve bins, we have a profile instead of just an average value, which some other methods of determining optical turbulence are able to resolve. You'll also notice throughout this presentation this symbol, CN squared, C sub n squared. And CN squared is the index of refraction structure function parameter, and it's a very common measure of optical turbulence, and it's the one that we'll be using also. So just to clarify, CN squared 1 refers to the optical turbulence in the first bin, which is the bin closest to the delta WX, whereas CN squared 10, the 10th bin, is the one furthest away from the delta WX. So the lowest bin and the highest bin, respectively. The traditional way of modeling turbulence in the atmosphere is using physical models, right? And there's lots of physical models that one can examine, but the two that we mostly focused on in this work was the Huffnagle-Andrew Phillips model, the HAP model, and the Navy Vertical Surface Layer model, NAVSLAM. So HAP, Huffnagle-Andrew Phillips, was derived from the original Huffnagle Valley model, which was created for the entire atmosphere. However, Huffnagle Valley did not perform particularly well. Andrews and Phillips found that Huffnagle Valley did not perform particularly well in the atmospheric boundary layer. And so they added a revised final term, which is highlighted in yellow there, which takes a reference CN square at a reference height h naught and uses the empirically derived 4/3 power to estimate CN squared throughout the atmospheric boundary layer. The NAVSLAM, the Navy Vertical Surface Layer model, instead of using a reference CN squared and then essentially extrapolating it up to a certain height, uses physical parameters, uses weather parameters to create a profile. And it does this using Monod-Nabokov similarity theory, or MOST, right, which classifies conditions of the atmospheric surface layer. And the atmospheric surface layer is the layer of the atmosphere where height has a significant impact on the turbulence in the atmosphere. So these two models use different methods of determining CN squared, and NavSlam only goes up to the first 100 meters of the atmosphere because it's used for the surface layer, right? Whereas HAP goes throughout the entire atmosphere because it was originally designed for that purpose. So before I go on and show you some of my results, I want to classify 3 regions that are of interest to us, right? I've classified these regions based on the level of turbulence, right? Because from an operational perspective, we care most about where turbulence is highest. Where turbulence is highest is where an optical system is least likely to be effective. It's least likely to achieve whatever mission it is that it's trying to do. And so we've classified this as the red region because that's where we care the most about. We care about accuracy in this region so that the naval commander can accurately tell when their laser weapon system is not going to be effective. And these are the probability distribution functions at each bin of the delta WX's observations. And these regions, the green, yellow, and red regions, were determined using the mean and the standard deviation of the entire data set, just to identify the top quarter or so of the observations and how different models performed in this region. The other plot on this slide you'll notice is the mean and standard deviation as height increases of the delta WX observations and of the HAP and the NavSlam predictions. So the one notable trend here is that all of the models decrease with height, which is expected, but it's not a surprise at all. However, NavSlam, which is these pink triangles here, consistently underpredicts the observations, the turbulence observations in the atmosphere. And this is also not particularly surprising if you have an understanding of the assumptions in NavSlam. So NavSlam was designed for the open ocean environment. Typically, the open ocean has lower turbulence than a terrestrial environment would. Since we are operating in what's known as the near maritime environment, where land and water both have an impact on the meteorology and both have an impact on the turbulence, the state of turbulence, then it's plausible that the turbulence will be higher than in an open ocean environment, which is more homogeneous than the near maritime is, because the near maritime is very complex. And so clearly these physical models have some limitations in predicting turbulence and classifying turbulence in this environment. So that's why we look to statistical models, more specifically regression trees, in order to try and evaluate this environment. Regression trees have been used in the past, notably random forest architecture has been used in the past, but in this environment, but it has not been used with any kind of vertical component to the problem. And so that's what that's the gap we're trying to fill with this project. So the first arrangement of data, we used a couple, but the first arrangement of data that we used in order to evaluate this environment was using height as another predictor, just like we would use temperature or pressure or the air-water temperature difference as predictors. We inserted height in there as well. And we also used a prediction from the HAP model. We used the prediction at whatever height from the HAP model as a predictor as well to see if inserting a physical model as a predictor would improve the performance, which this has been done in the past with a different physical model. So we wanted to see if it would continue to improve the performance in the vertical profile. The other arrangement that we have is we trained a separate machine learning model, a separate random forest model, and a boosted model as well for every bin. So there was 10 models that were produced. And we did this in order to look at some of the effects that height has on the parameters and the performance. And this model gave us more specific information about that. So first going into the model that used height and HAP predictions as predictors, inserting HAP into the model had a notable improvement to the performance. So the in the entire data set, the HAP, the model that used HAP showed improvement, but also notably in the red region where we care about turbulence the most, the HAP also had a significant improvement to the performance. Over on the right side of the screen, we have the parameter importance evaluations of both of the models. So this model here with the large blue bar, that indicates the amount of predictive power of the HAP predictions. And you see that the HAP predictions were accountable for about 56% of the predictive power of this model, so a rather significant portion. The red on each of these stacked bars indicates the importance of height to the predictive power. And it was 12% and 30% respectively. And this, again, like I said earlier, is not particularly surprising, considering that in the surface layer, height is expected to be significant to the optical turbulence. However, we wanted to examine how different parameters were important throughout the atmosphere. So that's why we turned to the other arrangement of the data in order to examine this problem. And we find, also unsurprisingly, that the air-water temperature difference is very important throughout the entire atmosphere. And as we talked about earlier with the buoyancy discussion, it is this air-water temperature difference that drives eddy formation in the atmosphere. So we would expect the air-water temperature difference to be significantly important throughout the atmosphere. Other important parameters include the air temperature on the red bars there, or the air pressure, which are the green bars there. But one of the more interesting parameters is the solar irradiance, which are these pink bars here just to the right of the air-water temperature difference. And you'll notice that the solar irradiance had a sharp drop-off after the first couple of bins, which has a reasonable explanation as well. So in the lowest bins, where the solar irradiance is heating the water, that is where turbulence is going to be most reactive to the solar irradiance, because that's where solar irradiance effects are taking place. Versus higher up in the atmosphere, where the solar irradiance dropped off significantly in its parameter importance, the sun is not heating the air any appreciable amount. Most of the heat from the sun is getting to the air via the heat transfer at the lowest bin. And if we look at this is for the random forest model. This is the analysis for the random forest model. But if we look at the boosted model instead, we see similar results, right? Air-water temperature difference is important, and there's sharp drop-off in solar irradiance. So if we then look at the performance of these models as they go up in height, we'll notice that the HAP model in particular, and also the NavSlam to an extent, although because the NavSlam is only able to predict up to 100 meters, it was capped at the fifth bin. We weren't able to observe what NavSlam's predictions would be in bins 6 through 10. But we noticed that the HAP model improves in performance from the 4th to the 10th bin rather significantly. Its performance is still far lower than any of the machine learning models, which is expected because these machine learning models were created for this particular environment, whereas HAP and NavSlam were created for other environments, and they have other assumptions baked in that may not necessarily be true in this environment. But all of the machine learning models had consistent high performance throughout the profile. Likewise, in the 3 regions of interest, the green, yellow, and red, and in the entire data set, the machine learning models had particularly good performance in these areas with respect to, as compared to the physical models. You can see the physical models have very large root mean square error versus the very small root mean square error between the machine learning models and the physical models. So talking about a few of the things that we can gather from all of this data that I just threw at you all, the first thing you observe is that the parameter importance aligns with our physical understanding of the atmosphere. It aligns with Mona Nabokov theory's predictions on how the atmosphere will behave. We expect the air-water temperature difference to be important, and the parameter importance indicated that it was. However, the physical models that were based on Monod-Nabokov theory still did not have as good of performance as we would have liked. We would have liked for the physical models to have better performance, considering they are based on these principles that we've found to be accurate, or at least that the machine learning model indicates is accurate. However, the combination of physical models and statistical models, i.e. using HAP predictions as an input, was a powerful combination. It improved the performance. In all of the regions of interest. The machine learning models consistently showed high predictive power throughout the entire profile. They were not significantly impacted by the height changes. They were not significantly impacted by the horizontal changes going across the path. And this suggests that if a model is correctly trained and adequately trained, it is able to give us accurate and consistent data, or predictive data, throughout its entire profile. So that's all I've got.
Questions from the audience?
Yes, sir.
What instrumentation did you have on top of the tower? What were you measuring?
So I didn't have any instrumentation on top of the tower. All of the weather data was taken locally from those two stations that I mentioned, the weather tower and the NOAA station. The way that the Delta WX made measurements of optical turbulence along this profile was using this effect. So this target board was made for the Delta WX to use, and this image is actually from the Delta WX looking at this target board. The Delta WX is what's known as a single-sided measurement device, so it only uses a single instrument to make turbulence observations, and this is different than double-sided methods such as scintillometers, right, which have a transmitter and a receiver. And the Delta WX observes these features and measures what's known as optical jitter at these features in order to resolve these 10 bins along the path. So the Delta WX, instead of looking at a target board and looking at the squares and the triangle on it, it'd be looking at the structural members of the tower, at the top of the tower.
Your half model, you had a parameter W. Was that the beam's waist? What was that?
That's the high altitude wind speed. Yeah, that's the high altitude wind speed, and we used a value of 21 meters per second, which is the value that's used in the Huff-Nagel Valley 5.7 model. And the reason that we use that is because that speed was validated in Huff-Nagel, and in the paper that HAP was originally introduced in, that was validated for altitudes above about 3 kilometers, right? And really the other terms in this model have a lower impact than this last term does in the atmospheric boundary layer. This last term is dominant in the atmospheric boundary layer. Yes, ma'am.
Thank you for the presentation. So basically, do this.
Yes, ma'am.
That would be like, if you look back, do you have any students when I continue?
Yes, I do. Yes.
Okay, that's
He's,
kind of
I don't think he's here right now, unfortunately. I think he has class. But
that's why I'm thinking now, to kind of tease out like what is coming up.
okay.
For the
Yeah.
next generation. But to introduce that aspect, what the other person will do, what do you think, I suspect that WX is just giving you the data and you just put it in histograms that you show.
Yes, ma'am.
In terms of NAVSLAM and HAP, you used the Navy provided software, or did you code?
So NavSlam has its own code,
Yeah,
and
you You just said.
Yes, yeah. I just entered in, so I didn't edit that at all. HAP, I just wrote this in a line of MATLAB. Yeah. Yes, ma'am. Yeah, I just wrote this.
Yeah, basically, I don't know if you noticed, but when I asked the speaker last year, he had so many hurdles. What was your hurdle? What the next person would have to solve that you are foreseeing as a
I think my hurdle was, and this is something I think a lot of Tridents experience, is just learning how to be healthy about my workload. And I know that's maybe not what you were looking for, but like I had certain expectations about how working on Trident would work and how working in research would work, and they proved not to be entirely true. Right, my workload came and went in waves, right? And if I could do it over, I'd probably arrange it to where it was a little more consistent, so that it wouldn't disrupt other parts of my life. But from a research perspective, the issues that we ran into was it was deciding which directions to go. Because with work like this, there's so many different directions, so many different specific parts of the problem that one could pursue, and trying to figure out which of those is the most important and the most doable ones to look into was something that it took a long time for us to figure out, and we're still figuring out in some degree. I mean, this project's not exactly done. I'll be working through the summer and whatnot, and that question is not entirely answered. But for the purposes of this presentation, we settled on this red, yellow, green question. I hope that answers your question.
I was hoping that you would say a little bit more about machine learning experience.
Oh, yes.
Things that you developed those
So
used, kind of pre-made.
yeah, so they're based on Scikit-learn's API. So I did not write all the for loops and whatnot that would be necessary for the machine learning, but Scikit has a lot of flexibility in what you can do with it. So I did all the hyperparameter tuning, and I mean the machine learning models performed surprisingly well once the data was correctly aligned. The pre-processing of the data is really what took most of my time, but once the pre-processing was done, and I put them into the model, and they sat there and trained for a couple days, it really was not particularly difficult. But it did take some time learning how to use it. That took up a significant amount of time teaching myself how to do that, because I'm a mechanical engineering major. I don't come from a machine learning background, so I had to kind of figure that all out. Thank you, ma'am. Yeah, what's up?
Jeremy, I thought you did really well. It's been really great seeing you work on this for so long and seeing it all come together so nicely. It's like amazing. I wanted to ask you about your plans kind of moving forward with your career and then going to graduate school for civil engineering, right? So you mentioned this is kind of more data processing side. How does that translate to your graduate program? Is there some sort of correlation between what you've worked on for so long to what you're going to do in graduate school?
Not much, frankly, but a lot of the soft skills that I learned in this research process, I think, will be very useful. Right, learning how to write a lot in a short amount of time, how to put together a presentation, how to tell a story with the research, that kind of thing, is certainly something that I had no experience with before this, or no meaningful experience. And so those kind of things will be useful, certainly for research, but also for my career as an officer, right? This is not the last time I'm going to do a presentation, and I'll probably do it in front of bigger crowds in the future. So those kind of things will be useful. I'm certain of it, even if my future research may or may not be quite as data intensive as this project was. Is there another question? Sir?
Okay, great. Surface observations from the sailing center.
Yes, sir.
Do you think the process and the model would be improved if you had greater fidelity and atmospheric boundary layer. So wind speed, for instance, it isn't constant.
Right. Yes, it certainly is not, and I didn't have time to address it, but even in this, let's see, this one doesn't show it as well. This one shows it much better though. It dropped by like almost half within the first 2 bins. It's this parameter in accordance right here. So certainly that's the case. I'm sorry, what was your question again? I got caught in that.
Greater fidelity and sort of the change in these parameters within the boundary layer, would that improve protection?
You mean like taking weather data at the different bins kind of thing? Well, it may. We didn't explore that question, obviously, but frankly, the performance of the machine learning models did not seem to deteriorate with this separation distance, and that's really what I was trying to get at with that last conclusion, is that I don't think that is necessary. It might be helpful, but using local parameters, we saw very little decrease in the performance of the models, even in bin 10. Even in bin 10, the models performed just as well as they did in the second bin, right next to the delta WX. So I don't think it's necessary. It might improve it some, and that's something that a future researcher perhaps could explore. But this suggests that it might not be necessary. Yeah, what's up?
Do you expect there to be a sort of geographic dependence for some of these models? Like, for example, would a ship out in the West Pacific is the same model as what you developed here and there?
Absolutely, there's a geographic dependence, right? And that's exactly why in the title of this work I mentioned the near maritime, because it is highly geographically dependent, right? And that's why NavSlam. That's why NavSlam doesn't really perform that great in this environment, because NavSlam is made for the open ocean. It's made for being out in the middle of the Pacific, right? NavSlam's not made for being right next to land or being in a canal, right? That kind of thing where the land and the water have this complex interaction between them. So certainly this is a geographic question just as much as anything else. And the particular geographic setting that we explored was the near maritime, because that's where we are. It's the near maritime. So does that answer your question?
There's no other questions, let's thank our speaker. We have about 5 more minutes before the next speaker.
Good morning. My presentation is titled Analyzing CN Coma Morphology to Investigate Correlations Between Cometary Age and Dynamical Classification. My advisor for this project was Dr. Matthew Knight. So the overarching goal of this project is this was an exploratory study, and we had a large imaging database of roughly 79 comets that we were looking at, and all we were looking for was a variance in the structure of these images. And our end goal was to evaluate what a comet's evolution looks like, which I'll talk about in detail later. So why do we care about comets? What are comets? Who even cares? Comets are renowned as fossils of the solar system's formation. So roughly 4.6 billion years ago, when our young sun was forming, comets formed right at the edge of this protoplanetary disk, and they were preserved from the young heat of the sun and then perturbed into reservoirs far from this heat, and this has preserved them as fossils of the solar system's formation. For this project in particular, we were using new filters that Professor Knight and his collaborators have been using for the past decade or so that are known as narrowband filters, and these allow us to isolate individual gases coming off of a comet. Lastly, our third, this is one of the few broad-scale analysis done on comet studies. Usually analysis of comets is done on one particular comet where as much data as possible is gathered for that particular comet. And comets that don't have a lot of data, there's just no published work done for them. The last overarching goal of this project was to study a rarely studied cometary class in Halley-type comets. You may have heard of Comet Halley itself, and that's actually a member of a cometary class that I'll talk about later. So what is a comet? A comet is often described as a dirty snowball because of its composition of frozen gases and dust that were preserved far from the heat of the young sun. It's composed of a central nucleus and then its surrounding coma, and then it often exhibits dust or ion tails. So the nucleus of a comet is only often 1 to 10 kilometers in diameter, and as the comet enters into the inner solar system and approaches the heat of the sun's heat propagates into the nucleus of the comet, and the gases and dust within sublimate off or transition from a solid to a gas, and what we're actually observing is the sublimation of these gases and dust from within the nucleus of the comet, and that forms the coma of the comet, which can be on the order of millions of kilometers in diameter. So when we're actually observing a comet and taking images from the telescopes, we're observing the coma, and we're inferring properties of the nucleus from what we're observing about the coma. And also in many comet images, you can see dust or ion tails. These often appear as streaks in the image, but these aren't important for the application of our project in particular. So I mentioned that comets formed roughly 4.6 billion years ago at the edges of this protoplanetary disk, but after this initial formation, comets were perturbed into two primary reservoirs, the first of which being the Oort cloud region. This is a large spherically shaped region on the order of 20,000 to 100,000 AU, where an AU is the distance between the Earth and the Sun. So this is a very large region, and it's a three-dimensional sphere. The second region which comets were perturbed into is the Kuiper belt region, and this is a flat, disc-shaped region, so no inclination, that's on the order of 30 to 50 AU, so just beyond the orbit of Neptune. So this is an example of a comet that would originate in the Oort cloud and what its orbit would look like. As you can see, it's inclined, and it could come from any direction in that 3D region, and they're often called long-period comets because their orbits are much longer because they come from such a larger region. An example of a Jupiter family or shorter period comet, which originates in that flat, disc-shaped Kuiper belt region, is shown here, and as you can see, it's on that flat inclination profile. So we often sort comets based on their dynamical classification, which is done using which origin region they come from. So as I mentioned, the Oort cloud is one of the primary reservoirs that comets exist in, and within the Oort cloud, there are further classifications for comets. The first of which is long-period comets. So they're called long-period comets because their orbits are much longer, and within long-period comets, there are dynamically new comets and returning Oort cloud comets. The difference between these is a returning Oort cloud comet is statistically likely to be entering into the inner solar system for the second time, whereas a dynamically new comet is statistically likely to have never entered into the inner solar system before. The third member of the Oort cloud family of comets is Halley-type comets, and this is that rarely studied cometary class. And these comets are on much shorter orbits on the order of hundreds of years rather than hundreds of thousands of years for some dynamically new comets. And they've been randomly perturbed into much shorter period orbits in comparison. The last overarching class is short period or Jupiter family comets. And these are the comets that are originating in that flat disc-shaped region. They're often called short period or Jupiter family comets because their orbits are gravitationally dominated by Jupiter. So what are we actually looking at in this project? So the overarching goal is to study structure or morphology. And when we talk about morphology, we're just looking at the variance in the coma structure, whether that be in gas or dust. So the main gas that we looked at was CN. And CN is chosen because it has a very bright emission line and it has a very narrow peak, and it allows us to isolate just that gas when we're imaging the comet. The other major filter we used was the R-band filter, and that allows us to image what's going on with the dust in the comet. So this is an example of the type of imaging we're looking at for a specific comet, where the red is the brighter source regions. So this is the coma that you're looking at. Red is more active or brighter regions, and then blue would be darker, less active regions. As you can see, there's two clear jets or regions that are kind of active here in this animation. You can see the top one's doing a sort of corkscrew motion as well as the bottom one. So what is comet evolution? So comet evolution is also often referred to as cometary age, but I mentioned that all comets formed roughly 4.6 billion years ago. So what are we actually talking about when we're talking about comet age? A comet age refers to how many times it's entered into the inner solar system and therefore been evolved by the heat of the sun. So an example of a comet that we've actually imaged from a flyby is shown here with 103P Hartley 2. As you can see, that white is the active region in this comet, and as you can see from the flyby, there's one active region when we actually went and imaged the comet itself. So comet age. It's inferred that a young comet would be active over its entire surface because the sun's heat hasn't propagated into the nucleus and is therefore just active over its entire surface, or isotropic. An intermediate age comet would be active over more patchy regions as the sun's heat is propagated into that nucleus and some of the gas and dust has been released off, but there aren't clear, distinct active regions that we would see in an older comet. So the actual data used in this project has been compiled over 16 years from Professor Knight and his collaborators from June 2008 to December 2024. 4 new comets were observed during 2024, which I'll get into detail about. Out of the 79 comets that we have on over 1,600 nights, 34 are classified as short period comets, 19 are dynamically new comets, 21 are returning Oort comets, and 5 are those rarely studied Halley-type comets. I'll also go into detail about what we're talking about in terms of radial profile slopes. So how do we get these images that you've seen throughout this presentation already? So when we take an image from the telescope, it looks something like the one on the left there, where you really can't see any observed structure. You just see one bright region. So we use an enhancement process known as azimuthal median division. And what this does is it looks at the centroid of the comet, and it goes out a certain radius. And at that radius, it takes a median of the brightness. It does that for every annuli, and then it subtracts it from the original image. And we end up with our final enhanced image that looks something like this, where again, you can see that the white is the more active regions, and the darker areas are the regions that aren't active. We use various facilities to acquire this data, the first of which being the Lowell Discovery Telescope in Flagstaff, Arizona, which is a 4.3 meter diameter telescope. Also in Flagstaff, Arizona, we use the Hall 42-inch telescope. Our source of imaging from the southern hemisphere was the Southern Astrophysical Research Telescope, which is a 4.1 meter diameter telescope. And we had to apply for time through an application process at this telescope. And lastly, we used Hopper Hall's telescope, where we also have one of those narrowband filters now, to get some of the data in this database. There's Professor Knight and I at the telescope. So as I mentioned, 4 new comets were acquired during 2024, and I'll go into a little bit of detail about each one. So the first of which was 2021 S3 Pan-STARRS, and this is a returning Oort cloud comet. On the left, our R-band imaging, or our dust imaging, is always in the gray scale, and on the right, our CN, or gas imaging, is always in the brighter red scale. So this comet looked promising. As you can see, 2 distinct clear jets on each imaging, but unfortunately, we were only able to get 1 night of data due to weather at SOAR as well as limited observing availability, but this was still of statistical significance for our specific project. The next comet observed was 2023 H3 Shushishan Atlas. As you can see, the structure of this comet looks completely different. You can see one broad hemispheric region of activity in both the CN and R-band filters. Most significantly, we were able to observe 2 Halley-type comets this year. So we only had 3 total Halley-type comets in this database before this year, and the addition of 2 more is statistically significant. This was 13P Olbers. The 2 images on the left were before its perihelion, or closest approach to the sun, and the images on the right were after its perihelion. As you can see, the structure changed significantly after it approached the sun. We acquired the most data for comet 12P Pons-Brooks, our other Halley-type comet. So what we were interested in doing here is we found a rotation period, or how long it took for the comet to rotate one time about its poles. And we do this by matching up images where the jets look like they're in the exact same region. So the top 2 images, you can see the jets are oriented in the same way. Bottom 2 images, the jets are oriented the same way, the same for these 2. And then we calculate the time difference between each of those 2 images to get a measure of how long it takes for the comet to rotate one time about its poles. The first chunk of the semester was spent getting a standardized format to view these images. And we generated a Python script that took information from the FITS header, and the FITS is just a standardized astronomy format. And it took information such as the name of the comet, the date it was observed, and then the filter being used, and then it color-coded by the specific filter. It also allowed us to apply Gaussian smoothing, which essentially just, for comets with low signal-to-noise ratio, just improved what the image actually looked like. From there, we compiled various parameters from the online resources, NASA's Jet Propulsion Laboratory and the Minor Planet Center. The type of things we collected from there were the dynamical classification of the comets, the perihelion distance, or closest approach to the sun, the heliocentric distance, so the distance from the sun when they were observed, the geocentric distance, the distance from us when the comet was observed, the period or length of the orbit, the Tisserand parameter, which is a measure used to classify the dynamical classification of the comet, and the reciprocal original semi-major axis, which is a way of distinguishing between dynamically new comets and returning Oort-Cloud comets. We went on to quantify how many jets were observed for each comet, and then I'll go into detail about the comet radial profile slopes. So jet quantification. So when I mention a comet jet, it's kind of a broad term for a region of defined activity. So we went through, and for each night, we quantified how many jets were actually observed. So for comet 154P Brewington in this specific image, you can see there's just kind of one broad region of activity, so we classified that as having 0 jets. For 81P Wild, you can see the white arrow points to the one singular jet. 12P Pons Brooks is the comet I just showed. There were 2 distinct jets. And then 2014 Q2 Lovejoy on a few nights had 3 distinct jets. So we went in and did this for all the comets in the database. The other overarching thing we were interested in is where comets that didn't have any observed structure, we wanted a way of quantifying what was actually going on with those comets because we couldn't visually see what was going on. So we were interested in what we called the coma radial profile slope value. So I mentioned that to get these final enhanced images, we had to subtract off this bulk brightness profile, which was just a measure of how fast the brightness falls off for each comet. So we took this bulk brightness profile for each comet, and we graphed it. A steeper value, a steeper absolute magnitude for the coma radial profile slope meant that the brightness fell off faster in comparison to a shallower slope value. And we were interested to see if these slope values had any correlation to any of the parameters that I mentioned before. So this ended up being our most interesting plot. So on the x-axis, we have the R value CN radial profile slope, and on the y-axis, we have the CN or gas radial profile slope. We then color-coded the comets. This was roughly 340 data points. We then color-coded the comets based on what dynamical classification they were. And we saw that there was a clear trend in what was going on with this data set. So we saw that Jupiter family comets were generally clustered in that top right region, whereas Oort-Cloud comets were generally clustered in the bottom left region. We have a few possible explanations for why this is, but we think it's mostly due to what we're calling icy grains, which is essentially when I mentioned that the heat of the sun propagates into the nucleus of a comet, the gases and dust within sublimate off. An icy grain would be a larger structure that sublimates from the nucleus, and then as it gets farther out, it sublimates again. And this would cause the slopes to be shallower in comparison to something like an Oort-Cloud comet where we're seeing the slopes are steeper. So we think most of the material is just coming straight from the nucleus for an Oort-Cloud comet. We made a whole bunch of other plots in the same manner, color coding by different parameters that we had compiled. This is one with orbital period length, and that essentially shows the same thing as dynamical classification because comets' dynamical classification is directly linked to how long their orbital period is. This was perihelion distance, or the closest approach to the sun. So generally, most comets are observed at have fairly similar closest approaches to the sun, so this didn't really reveal much. This was quantifying by the number of jets, so 0, 1, 2, some had 3 jets. This, again, doesn't really show us much in this form, but I'll show another form later that revealed more. Tisserand parameter, so this is just a measure of how strong Jupiter's gravitational pull is on that comet, and this is essentially how they sort by dynamical classification. So this, again, reveals a very similar thing to dynamical classification, but in a less straightforward manner. And then this is the one over the reciprocal semi-major axis. So this is a way of sorting between dynamically new comets and returning Oort-Cloud comets, and we didn't really see any clear correlation in this plot. So there were a few things we're concerned about with our initial plot that could be affecting the trends that we're actually seeing. So we didn't take into account how far we were when we observed the comet and how far from the sun the comet was when we observed it. So we think the distance from us could be directly affecting what's actually going on with the data, because as you can see, there's a clear grouping in the top right versus the top left in terms of they were observed at closer distances than the comets in the bottom left. And Professor Knight and his collaborators are going to work to incorporate this into the original data so that we make sure that any correlations that we are seeing aren't being caused by this. The other thing we looked into was, do comets exhibit different slopes on different nights? So for the vast majority of comets, they had fairly tight clusterings of what slope values we were seeing, whether it was over multiple nights or multiple months even. But for some comets, such as 2007 N3 Lulin, we saw a pretty wide range in what the slope values looked like over a long observing period. And we think this could be directly linked to the observing distance when that comet was originally observed. So that's something that when we take into account the observing distance, we think that will decrease that clustering. I mentioned briefly that we wanted to have some metric of seeing what was going on with the number of jets that we observed. So we just made this simple bar chart that just shows how many jets were observed by dynamical classification. And we saw that Oort cloud comets exhibited 2 jets much more frequently than Halley-type or Jupiter family comets. We have no real clear reasoning for this, but this was just what we saw. So a summary of the results. We saw that there was a clear correlation between the gas and dust slopes of those coma radial profiles. Jupiter family comets exhibited much shallower slopes than that of Oort cloud comets. We think that that original graph that I showed you could be a useful metric for sorting where Halley-type comets fall in terms of their origin region. So I mentioned that we think Halley-type comets originate in the Oort cloud, but there are some ideas that say maybe they don't actually originate there, and we think this could be a useful way of determining what's actually going on with Halley-type comets. There are some extenuating factors that we still need to take into account with this data that Professor Knight is going to work before we make further broad-scale analysis of what's actually going on, such as the distance from us or the distance from the sun when the comet was observed. I mentioned that the slopes were fairly consistent over multiple nights of observing. And then lastly, the morphological analysis that Oort cloud comets exhibited 2 jets much more frequently than Jupiter family comets. Thank you, and I'll take any questions.
Questions from the audience?
Can you go back to the picture you had of the model? Just wondering, can you say a little bit more about the model? What assumption, what parameters, what assumptions? How do I go through them?
Yeah. So all it does is it starts at this, we pick a centroid of the comet, where we think the centroid is or where the algorithm thinks the centroid is, and it just goes out 1 pixel. And then it takes an annulus at that pixel, and it takes the median of the counts at that pixel annulus. And then it just keeps track of what that median is. So that's why you see a variance in the brightness of the model, because it's literally just taking a median at each distance from the centroid.
Does it usually look so Gaussian? It looks nice and smooth.
Yeah, for the most part. It's just the model subtracted from the original. Yes, sir. Yes.
So you said you used 4 different telescopes for collecting data in this research. I'm wondering specifically how the Opera telescope seems not as complex as the ones in Arizona and South America. So what exactly did you use that for? That differentiates it?
Yeah, so it was the data itself was the exact same. So we just took images in the CN filter as well as the dust filter, but the Hopper telescope was just a much smaller diameter telescope. So its capabilities are just much less than that of those other much larger telescopes. But it can be useful for something like this because we're not necessarily always just looking at, we don't necessarily need high signal to noise ratios because we're not always just looking at the structure if we're looking at a quantifiable measure such as the radial profile slopes. Yeah.
I'm wondering, did the number of jets have anything else to do with just like what type of comet it was? Like, does it have to do with its age, or was that just something you noticed?
Yeah, so we didn't make any sort of broad correlation between the number of jets and what was going on with the age or evolution of a comet. That's something that we're definitely going to keep looking into in the future. But yeah, we didn't make any sort of correlation that shows, yeah, for certain if it displays this many jets, it's an older comet or a younger comet. Yes, sir.
Well, congratulations on this work. I enjoyed your talk. The species CN, is the motivation to study it because of its prevalence in comets, or it's certainly atypical and unusual for those of us used to, thinking about terrestrial atmosphere and the kind of species we might encounter, is it representative of what's true in comets, or is it like a ease of study, ease of analysis that makes it attractive?
Yeah, so it's generally because of the ease of study and ease of analysis. So CN itself doesn't actually exist within comets. It's actually HCN. So it's a daughter species. The reason it's chosen is primarily just because of the bright emission line and having such a narrow peak. Yes, sir. Yes, sir.
On that slide you had a couple minutes ago with the filter on it, if I'm understanding, you want to get the background out as much as you can so you can see the comet. Could you take out more, like what are these like rectangle things and the streaks that are going through here? Do we know what those are? Can they be taken out too?
Yeah, so the streaks are usually generally stars. Yeah, stars are other artifacts in the image because most of these CN images are exposed for roughly 5 minutes. So any star or something streaking through would be visible in the imaging.
Would it be helpful to take those out?
It doesn't really affect our study because when we're actually looking at the data, we only go out to a certain portion of the from the nucleus.
Thank you, Professor Schroeder. As she mentioned, my name is Midshipman First Class Owen O'Malley, and today I'll be presenting my research on using machine learning for underwater optical turbulence and vortex beam characterization using multimodal synchronous measurements. Here's an overview of the 4 stages of this presentation. The first, I will go over some of the motivation for the project. Then I'll go over the experimental methods that I use. Next, the results of the machine learning models that I use for beam classification and environmental sensing. And lastly, we will conclude and go over any questions that you may have. The Navy has invested decades of research into using directed energy weapons, communications, and sensing systems. For example, the USS Preble has the first US Navy laser system developed on a surface warfare ship, and they have demonstrated this past, earlier this year, the capability to destroy unmanned aerial vehicles, which is clearly of high relevance, especially given current events. A second application, which I'm particularly interested in as a future submariner, is with underwater optical communications. A challenge with communicating between submarines and something on the surface, such as an aircraft, is that sonar works really well underwater for submarines, but it doesn't propagate well in the air. Conversely, airplanes can use radar, and radio waves propagate well in the air, but they don't travel very far underwater. And crossing that boundary is particularly challenging. But blue laser communications is something that DARPA put out in their strategic plan all the way back in 2009, and this research is ongoing. And lastly, the Chinese government is investing research into what they call the Guanlan satellite, which stands for Sea Watcher. They are seeking to create a satellite that can detect submarines, such as US Navy submarines up to 500 meters deep, due to the benefit of using directed energy to penetrate both the atmosphere and the ocean. However, a major challenge of these laser systems, both underwater and in the atmosphere, is optical turbulence. All of these red highlights are sources of optical turbulence, and being able to characterize how this turbulence affects different laser systems is the point of my research project. Specifically, the type of laser light that I use carries what's called orbital angular momentum. And the reason why we are interested in this light is because they can create unique symbols, such as in the top left there. These beams that carry orbital angular momentum, there are different modes, which I'll go into later, but essentially you can superimpose different OAM states on top of each other to create these unique symbols, which could be a type of alphabet for a communication system. The reason why this works is because beams that carry orbital angular momentum, also called vortex beams from here on, have a wavefront that's helical in nature. What I mean by that is, take this image to the right, which shows what's called a plane wave. If I look at all of my light waves and connect the peaks of all of my waves, the surface that connects those is a plane. However, these vortex beams, when I do the same thing, connecting all of the peaks of the waves, it creates a spiral along the propagation path. This creates a phase singularity at the center, which creates the optical vortex, or the hole in the center of the beam. So I use Laguerre-Gaussian beams, which are a type of beam a type of vortex beam. And the mode number, which I alluded to earlier, just corresponds to the rate of spiraling, where a mode of 1 corresponds to 1 full rotation per wavelength. And these different beams, the different modes of the beams are orthogonal, meaning superimposing these different beams can then be demultiplexed into their unique modes so that I can use multiple streams of communication in one beam. So the big question, how does optical turbulence affect this light that carries orbital angular momentum, which is a never-ending research project. It's been going on for decades. It'll keep going on for decades. This is just a snapshot in time and my contributions to the research. So the purpose of this project is to take these beams, propagate it through experimental underwater turbulence, and record multiple properties of the light on the other end. And then I have two main questions. First, can I take my distorted measurements and infer something about what beam I sent? Can I classify what mode was sent? And the second is, can I take these measurements of the distorted beam and infer something about the environment? Can I classify the turbulence strength that I sent my laser through? So those two main questions: what modes characterize the turbulence the best? Which beams can I use to best sense the environment? And then what properties are the most important also? And then the main challenges of the research are that we have to send multiple different beams through the same turbulence, and turbulence changes rapidly. So we need to come up with a way to be able to compare the performance of these different beams through the same turbulence, which I'll mention how I do that. So next up, the experimental methods. First up, we'll talk briefly about what optical turbulence is and how I generate it experimentally. So on the top left there, we have those lines that are denoting a plane wave, which I mentioned a few slides back. And when that goes through turbulence in the atmosphere, which cause random changes to the refractive index of the medium, that distorts the wavefront and distorts the image. So refractive index, largely affected by temperature. So the way I create that turbulence is with a Rayleigh-Bernard tank, which is a water tank that's heated from below and cooled from above to create natural convection that mixes up these different temperature gradients. And then lastly, the effect of these phase changes that the refractive index variations cause, that is what causes the distortion to the intensity of the light via interference of those waves. And almost 3 years ago now, I had an internship where I simulated Rayleigh-Bernard turbulence on the Department of Defense high-performance computers at the NASA Stennis Space Center. This was before I even knew about this project. But later that fall, one of my mentors on the crew team reached out to me and was like, "We have a Rayleigh-Bernard tank that we send lasers through. You should come join this project." So just a fun trip down memory lane with that simulation. So the different properties of the beam that I measure, in this presentation, I'll largely talk about two: the pupil plane intensity, which is the intensity of the light that I measure with a camera if I just take a white backboard that has the light on it and I take pictures of that. And the second is the mode sorter decomposition. This is an optical tool that takes the helical wavefront of the beams that carry orbital angular momentum and split it apart into a transverse distribution. So this spot, which is the output of the mode sorter, actually moves left and right depending on the mode that I send through. So it's useful for beam classification. And then for the environmental sensing, I also use the phase distortions of a Gaussian beam. That's just the flat wavefront beam, and that is used for the environmental sensing as a feature. So here is the diagram of how the experiment runs. The big takeaway here is that I send 8 beams carrying different modes of orbital angular momentum, and I have to cycle through those beams really quickly before the turbulence turns over, which in our case is 0.67 milliseconds to get through a full cycle. And then also synchronize the device that creates those beams with the cameras that record it. That was a challenge of the project that we successfully achieved. So next up, we'll cover the results of the project, going over how I designed the machine learning algorithms to both classify the beam that was sent and classify the turbulence that it was sent through. So looking at the pictures on the left here, these delta T's are the gradient between the Rayleigh-Benard plates. As we can see, as the difference in temperature increases, we can visually see more distortion. But we want to see, can I input this to a convolutional neural network, and can I accurately figure out what level of turbulence it was sent through? So this is a version of the machine learning network that has been used in research past. And in future iterations of this model, I put my own twist on it, which I'll show in a minute. But it takes a single image of the input, a single input of the image, and then there are multiple convolution layers that extract features of the image, and then I output it into 4 classes, the no turbulence case up to the strongest level of turbulence. And I do this for all of the beams that I sent through. So I train one network for the Gaussian beam, one network for the mode 1, and so on. So I'm trying to see, do different modes of the beam classify the environment in a different way? Are some beams better at sensing than others? So like I said, I trained 8 different networks, one for each beam. And I made confusion matrices to show the accuracy in its classification. And then summing across these rows shows the predictive accuracy for each case. And then I dump those into these bars. So the Gaussian row is that data there, and then the 8 other, or the 7 other modes are shown also filled in. And we see that the non-negative modes, so from Gauss to +4, all have similar accuracies, but the negative modes take a bit of a hit, especially the -3. It is misclassifying those 3.19 data points. So the conclusion that I came up with is that the positive OAM modes and the Gauss provide similarly effective information using just the pupil plane intensity. But this is a multimodal study, meaning I'm taking multiple measurements to try to see if multiple features together can improve accuracy. So here I'm also taking the phase distortions of a Gaussian beam to see how does that do in predicting the level of turbulence. Note the color bar here. It's not an equal scale. So that bottom right goes from -6 to +6. There are much greater phase changes there. However, what I'm really interested in is what if I stick both of them together? So this is where I came up with the cheesy name OwenNet, because I guess it's popular to stick your name and then net. But I take that first network with its convolution layers, and then a second parallel branch. So each branch is identifying its own set of features on the 2 images, and then I concatenate them and then classify between those 3 levels of turbulence. And what I see is that with the pupil plane only, so this was like what we, like that previous example that we were showing, where I'm trying to classify with just the pupil plane. I also do the same with just the phase, and the phase only doesn't classify the environment as well as the pupil alone. But when I stick both of them together, I get 99.5% accuracy classifying between these environments, which is a significant upgrade from either one alone. And I want to make it clear that this isn't just taking 2 different predictions, the pupil prediction and the phase prediction, and then figuring out which is the more confident or which is the better prediction. It's actually taking 2 orthogonal viewpoints and using those together to come up with a better prediction altogether. So next we're moving into our beam classification application. And the big question here is, does this mode sorter, the spike translating left and right, does that help us? But I really want to extract just a single feature from this, the centroid of this mode sorter, because that's what it's supposed to tell us. The translation left and right is the feature of interest. So the way I do that is I take a cross-section where the mode sorter spike is prominent, and I can see that for the modes -4 to +4, I can see the cross-section plotted here. And it seems pretty promising that it should be able to identify the mode based on where the integrated centroid of this curve is. So taking essentially where the maximum value of this peak is and seeing where it lies, is that a good feature for beam classification? And based on the correlation between the mode and the centroid of the mode sorter, it seems like it would. We see clear bands separating different modes when I plot the mode sorter centroid. And for when I turn the turbulence on to the weakest case, what I love to see here is that the bands, look at the purple Gauss band fluctuating up and down, and then above and below it, you can see the modes 1 and 2 following those same undulations, showing that these beams are propagating through, at least in this case, a frozen environment, meaning each beam is seeing similar enough turbulence such that the distortions on the mode sorter are similar. And as the temperature gradient increases, the correlation between the mode number and the mode sorter centroid does go down, but it is still pretty high for the weak levels of turbulence. Essentially what this is saying is that the bands are pretty clear even in weak turbulence. So now back to our machine learning networks. I can take one network that just takes the pupil plane image in and tries to classify which mode it is. In this case, it's the Gauss. We can tell that from our eyes. But ONNet 2.0 takes not a second convolutional branch, but the feature of this mode sorter, which is the centroid of it. And now I concatenate those together to see if that performs better than just the pupil plane alone. Sort of the training conditions that I use for this, I really want to ask if training in one environment, meaning my weak turbulence or my medium turbulence or my strong turbulence, does that trained network provide accurate results in other environments? Meaning, can I carry over those results to other turbulence conditions that I haven't seen before? And then the second question is, does the mode sorter data improve the accuracy? So here are the plots that I'll walk through now to show the results. So the single input prediction, that's just the pupil plane image. Each graph is showing a different training setup, meaning am I training it on the weak turbulence, the medium turbulence, or the strongest turbulence? And then each different color is showing the classification accuracy, classifying between the 8 different beams in the different environments. And what I notice is that in the easy training conditions, it's getting the no turbulence, and the turquoise is the easy 1.26 degree. It's getting those really well, but it's not carrying over to stronger environments as well. Versus if I train in the strongest level of turbulence, look at the dark blue where there's no turbulence. It should totally be able to distinguish between those, but it's not. It's learning, its training data are too hard for it to actually pick up what the different modes look like. But in the medium case, we get the highest accuracy. So this data is being trained on the yellow turbulence bar. And that has the best average carryover to both the weak and the strong environments. So the easy mode and the hard mode don't perform as well as kind of the Goldilocks region, which in our case is the 3.19 degree case. And then the multi-input prediction is when we add in that mode sorter feature. It doesn't perform any better. In fact, in most cases, it performs worse, which was kind of a shot to the heart for me because I really wanted this mode sorter to help us out. But I tried changing the training settings and a lot of different things, changing the network hierarchy, and it just didn't perform as well, showing that the pupil plane image is really the kind of the money feature that's providing all the important information, and the mode sorter just isn't as useful. Maybe if I were just using weaker turbulence, where I could see those bands really well, maybe it would help there, but in the stronger turbulence, it just doesn't work. So train in medium conditions, and the mode sorter doesn't really help us. So now we'll go over some conclusions. So I created an environment, the Rayleigh-Bernard turbulence, where different beams could be sent through frozen turbulence and measure synchronous measurements of different properties so that I could input that into a machine learning algorithm. My machine learning algorithm for environmental sensing showed that different OAM modes perform similarly for the non-negative modes, but the negative modes did not classify the environment as well. Also, the phase and the pupil plane of the Gaussian beam synergize to enable the best environmental sensing application, or best environmental sensing results. And then for the beam classification, we want to train in moderate turbulence and try something else with the mode sorter. What I did with the centroid did not work. So these are just a list of other achievements that I've accomplished during my time as a Trident and the couple of years that I was doing this before that I'd be happy to talk about during the Q&A session, but I intentionally left out of the slideshow for sake of time and so that I could dive deep into the topics that I wanted to share today. And then I'd like to acknowledge PEO, Integrated Warfare Systems. They funded our optics table, which is a huge help. If you do anything with optics, you want to be able to mount the optics to a table rather than just kind of stick it on a desk. So that was super useful. And then the Trident funders. But also thank you to my team, especially Professor Avramov Zamrovich. She has been doing this for so long, started this research well before me. Maybe Lieutenant Jarrett is on the live stream right now. Thank you to him for introducing me to this project. And all of these midshipmen are carrying forward this project, and I'm so proud of them and what they will accomplish. And that's all. If you have any questions, thank you.
Questions from the audience?
Yes, we'll go to Dr. Malik Madani.
Maybe you had it on one of the earlier slides of I missed that. Did you show the gas level? Where does M show up in that thing? And what do you mean by positive versus negative?
Okay, yeah, I don't have the formula in those slides. Let me see if in any of my backup slides I have that.
Oh my God.
No. Essentially, there's an e to the im, either phi or theta. So the e to the I theta represents a rotation, and the m just scales that. So a larger m means more rotation, and then the negative versus the positive. That means am I corkscrewing clockwise versus counterclockwise?
So -5 versus 5, really, they're symmetrical.
Yes, and you bring up a very good point that the +1 and the -1, the only thing that that distinguishes them should be the rotation of the wavefront and not the intensity. However, what we saw is that the neural network was able to distinguish between positive and negative equal magnitude modes, which is totally counterintuitive, yes. But it just shows that the experimental work that I do has little errors in the way the spatial light modulator creates those beams, that a powerful CNN is able to pick up tiny little differences in how the SLM is creating that beam. I tried to get around that by adding some random noise to the intensity, and it still was able to pick it up. So honestly, I have no idea. And that's a limitation of machine learning, especially these deep neural networks that have so many layers that we can't really see what are you thinking. And so it is a bit of a black box, and that is a limitation of using machine learning. Thank you. Yes.
I know we're short on time, but if you could speak about your Gershberg-Saxon algorithm and kind of what you found with that, that'd be awesome.
Yeah, sure. So the Gershberg-Saxon algorithm uses a third modality that I measure, which is the focal plane intensity. So not only do I measure the intensity on the white backboard, but also the intensity through a lens. And the reason why that is useful is because propagating light through a lens performs a Fourier transform on the light field. And there is some math that explains how a lens performs a Fourier transform. But what the Gershberg-Saxon algorithm does is it's trying to retrieve the phase of these vortex beams. Retrieving the phase of the vortex beam that has a phase singularity at the center is really hard to do with traditional equipment. So this is an attempt to get around that. Essentially, it iterates between taking a Fourier transform of the pupil plane field with a guess of the phase, take that Fourier transform, which is trying to model what the lens did, so then I can reinforce the intensity that I measure in that focal plane, and then inverse Fourier transform, and then reinforce the intensity that I measure in the pupil plane, each time letting the phase do it at once. I give it an initial guess, but after many iterations, it tries to converge on the phase of that vortex beam. And in simulation, I was able to simulate Laguerre-Gaussian beams that have this phase singularity, and I was able to accurately retrieve the phase of the beams in simulation. So the left is the known phase from simulation, and the right is the estimated phase with the Gershberg-Saxon algorithm that I programmed into MATLAB. So it had no knowledge of the phase before, just the intensity in the focal plane and the pupil plane, and we were able to do that. Still a lot of challenges with getting that to work experimentally, but this research does kind of push steps in that direction. Maybe for you to discover next year.
Since I asked that question to the bar, what's your biggest rabbit hole? What do you try to get that question?
This. I spent probably the first entire semester on trying to figure out the Gershberg-Saxon algorithm, and I'm proud of the achievements that I made with it. And this work has been published. I've presented about this in conferences, but it certainly is a rabbit hole. It's a very hard problem to solve. It is not solved, but I can't thank you enough for Professor Avramov-Zomarovich is very hands-off. She let me fall into this rabbit hole for months, and maybe in February you dug me out. Yeah, but that was really her only hands-on moment with this in terms of guiding me where to go. So thank you for that. Thank you.
right, good morning, everybody. Thank you all for taking time out of your day to come listen to me speak about my Trident project titled The Application of Quantum Secure Encryption Algorithms in Bluetooth Tracking Devices. So I'm just going to start by running through what I'm going to go over today really quickly. So starting with a little bit of background as to why this project is important, what motivated us to kind of get into this project, and then I'm going to go into our first proposed implementation, the methodology, and the results. After that, I'll do the exact same for our second proposed implementation, and then I'm going to end with some conclusions that we drew from all of our tests and the results that we gathered. So starting with the background. You may have heard of a new invention on the horizon. It's called a quantum computer. This is a new form of computing that's based off of quantum mechanics. Principles of quantum mechanics such as superposition and entanglement allow it so that there is something called a quantum speedup, where these types of computers can perform certain complex calculations that a classical computer that we currently use cannot. Two of those calculations that quantum computers specifically are designed to kind of hit and solve are prime factoring of very large numbers, so taking a very large number and finding its prime factors, and then finding the period of some oscillating function. Well, the issue is that a lot of our current encryption algorithms that maintain our digital infrastructure are based off of these problems that a quantum computer will be able to solve. So, in the future, as quantum computers are becoming more scaled to a size that creates more risk for these encryption algorithms, we need to start migrating to a quantum safe environment. So this graph shows the projected timeline of a company like IBM, which is leading the charge right now in terms of quantum computer development. And it's showing their projected timeline over the next couple of decades for how powerful this computer is going to be. The number of qubits on the left side of the graph, that is essentially measuring how powerful this computer is and the complex calculations it can handle. And so if you see that the red highlighted portion, that is where we're seeing probably the riskiest part of the entire development of quantum computers, where they're going to start being able to break current encryption algorithms. So this is showing, experts believe about early 2030s is when we're going to start seeing this, but we're on track to kind of supersede those expectations, and so we need to kind of get on this now, as the timeline of early 2030s might seem far away, but in the global security landscape, that's actually very near in the future. So this creates the problem. We have to create new encryption algorithms that are quantum safe, and they're based off of different hard problems, as you see on the right. These are mathematical problems that create these algorithms and therefore dictate their characteristics. So the top ones are our current encryption algorithms. We have RSA and ECDSA, which I'll get into later. And the bottom four are the quantum safe encryption algorithms, which have been released and standardized, and society is starting to shift into usage of those algorithms. And so the big takeaway from this is that I want you to understand that the different mathematical properties, or hard problems that it's based off of, create different characteristics for these algorithms. So for example, if you look at the public key size of Crystal's Kyber, it's 1,568 bytes. It's much, much larger than the key size of the two non-quantum safe algorithms above it. This creates issues. We need to see if different technologies are going to be able to handle these different characteristics. One such technology is a Bluetooth tracking device, which a lot of you may have in the form of Apple's AirTags. The point that I want you guys to take away from this slide is the fact that it is extremely prevalent and very widely used throughout society. DoD members, everyday people, they all use them to track. I know people who use them to track their CACs. So they carry them around with them around campus all the time. And military teams use them for tracking shipments, fugitives, other materials. And so this opens up a lot of vulnerability for malicious tracking in the future. So to understand how we're going to shift the encryption scheme of Bluetooth tracking devices to a quantum safe state, we have to understand how this encryption scheme is currently laid out. So we have the lost device on the left. That is essentially the AirTag, or it could also be an iPhone, that is broadcasting some advertisement. This advertisement is picked up by a bystander device, so that could be my phone if I'm near some AirTag. And then that bystander device uses the public key that was being broadcasted to encrypt the location of that device. Then it sends that encrypted location report to a server, which can then, on the client side, be queried by the owner of that device. So they then get their encrypted location report, which they can decrypt locally to understand where their lost device is. The main takeaway from this slide is this advertisement on the left with the rotating public key is only 27 bytes worth of space. This creates a problem, because if you remember, I talked about how Crystal's Kyber, the quantum safe encryption algorithm that we're using in this project, is 1,568 bytes. How are we going to fit that into 27 bytes worth of space? So our entire project is centered around creating implementations of this encryption scheme that will be able to use the entirety of the Crystal's Kyber public key while still maintaining the 27-byte advertisement space, as this is hardware specified in the Bluetooth protocol. It's not something that we can just change on software. It's in all of our phones and all of our devices right now. So our first proposed implementation. It's perhaps the most straightforward and obvious answer, and it's to basically split up the entire 1,568-byte key into 59 different 27-byte fragments. So the device is broadcasting these fragments and rotating on some specified interval through them, where the bystander device is picking up the fragments and piecing them together to form the entire key. However, there's some immediate cause for concern with this implementation, because what happens if just one of those fragments is missed and you don't have a functional public key to encrypt the location? And even more so with our devices like iPhones, they're meant to save energy and save power. So they're not always listening on the Bluetooth channel for these advertisements. So some are going to be missed. So then can we foresee that and implement error-correcting code to manage that risk? And then if we want to ensure that this happens in a timely manner, we're going to have to rotate through these fragments extremely quickly. Well, is that going to, one, make it harder for the iPhone to receive those messages because it's rotating so fast? And two, is it going to destroy the battery life of the Bluetooth tracking device because it's not made to be rotating that fast? So the main device that we used in this project is called a puck. It's right here. It's a little small. It's essentially an AirTag, except I can connect it to my computer, write code and write programs that I can then upload onto the device so that I can have it function the way that I want it to function. So it's like an AirTag, except that I'm manipulating it to essentially create the encryption scheme that I want and then measure how it works and see if it's functional or not. So we first had to ensure that this was all working correctly, so we needed to look at a perfect environment. The device on the left is called a BLE, Bluetooth Low Energy Sniffer. It essentially connects to the laptop, and then you open up Wireshark, which is on the right, and it creates a perfect environment to listen for these advertisements. Every advertisement should be picked up. And so you can see I'm filtering by the broadcast, the advertising address, and it's showing the different broadcasts. And if you see this blue highlighted portion down here, you can see that the data that's actually being broadcasted, which I coded it to be this way, is all zeros and then a 17, which signifies the fragment number that I picked up. So in this case, we're looking at the 17th fragment of 59 different fragments. However, we needed to ensure that this was functional in a real-world scenario. Like I said, the Wireshark and the sniffer creates a perfect, ideal environment. So what we did is we developed an iOS app on my iPhone. Xcode is the development environment that's on the left, showing just a tiny snippet of the large code needed to develop this app. And the right side shows a screenshot from my iPhone of the app in action, listening for advertisements from the puck that is near my phone. The important part for this is that we had a unique identifier that was hard-coded into the payload of the puck that's broadcasting and being picked up by my phone, and we filtered by that. Because right now, Bluetooth is so saturated in the everyday environment that it would just start spewing all this information that I didn't want. So I needed to filter by the specific unique identifier that I coded on there so that I could only see the ones that I was concerned about. For this example, you can see by the identifiers that are popping up for each advertisement that's picked up, I got 1, 2, 3, 4, and then 6. So this is how I was able to see, based off of how fast I was rotating, these fragments, which ones and how many of these fragments were being missed. So in this case, it was 5, but it continues all the way to 59. And so getting into some of the results of this method. Like I just talked about, this is getting into how the app performed based off of the rotation speed that I had programmed for the puck. And so at about 7 seconds, you're seeing pretty close and pretty reliable 100% reception rate. But that is going to create, as I'll get to, another problem. So as we decrease down to about 1 second, we're seeing a reliable drop in the reception rate, where we're almost at about 50% on average for a 1 second rotation speed. So as we do start to rotate these fragments quicker, they are being missed more frequently. And so because of this, we wanted to see how long it would take for each of these rotation speeds for a bystander device to be, how long a bystander device would have to be near this Bluetooth tracking device in order to pick up the entirety of the key and piece it all together. And we did this also implementing error-correcting codes to account for the pieces of the fragments that are missing, so it can piece it together even if it misses some. But because the reception rate decreases as the rotation speed decreases, you need more extra fragments, basically, more extra advertisements to account for those extra missed advertisements. And so you can see with 7 seconds, we're almost at 8 minutes of having to be near a puck or a Bluetooth tracking device, which is just not going to be a feasible scenario, because this is more so we're passing by an AirTag or a Bluetooth tracking device, and we just want to pick up the key as a whole. We can't really expect a bystander to sit for 7 minutes, and even as we get down to 1 second rotation, 2 minutes is just too long to expect someone to sit within the right distance of a Bluetooth tracking device to be able to get the entirety of the key. And you might ask why we didn't go down past 1 second rotation speed. Well, here is why. We measured the battery life by setting parameters of rotation speed and broadcast speed on the puck and let it run until it died, essentially. And we saw that broadcast speed didn't really have that much of an effect on the battery life of the devices, except rotation speed. As we put it down to its max rotation speed of 0.1 seconds, we saw a battery life of 12 days. And you can extrapolate that, so about at 1 second, we're seeing 120 days, which I don't know about you, but I would not want to be changing my AirTag battery every 12 days. So for the best case of method 1, we picked a 1 second rotation speed. And the 1 second rotation speed is going to result in about 4 months of battery life. Still not that ideal compared to the about a year, even almost over a year in most cases for the current encryption scheme. And then we see the time for total reception, as I mentioned, is about 2 minutes. And again, that's just not going to be feasible for a practical use case that a company like Apple is going to want to have for its users. So the big takeaway is that method 1 is not a viable option for general use cases, while it could be for like specific research purposes. Getting into method 2. So this is going to be a lot more cryptography that we've pieced together a little bit more complicated encryption scheme that it looks a little bit more promising. So we start with the puck or the Bluetooth tracking device and some owner device that shares a master secret, which it then uses to create 2 identifiers, the key ID and the report ID, that it broadcasts in that 27-byte advertisement. So it can fit it in the advertisement, and the bystander device then picks it up. These IDs have associated counterparts stored on a server that the bystander device and the owner can query by. So the key ID is referencing a public key, the 1,568-byte key that I talked about, but it's stored wholly on a server. So we don't have to worry about fragmenting it, missing a piece. It's all on the server, and the bystander device can query the server by the key ID to then get the public key back in return. Then it encrypts the location and creates the location report using that then retrieved public key. And it sends that along with the report ID to the server, where it stores it in a separate database where the report ID matches to encrypted location reports, which then the owner can query by the report ID and get the encrypted location report back and then decrypt locally. So this solves the problem of the 1,568-byte key not being able to fit in a 27-byte advertisement, because instead we're storing it in a whole location as a whole and referencing it by the advertisement, which has an identifier pointing to it. And one of the concerns that we have with this method is the overall privacy. We don't want the server to know any information at all. We don't want Apple to know anything. We don't want them to essentially correlate information about which reports are being retrieved by different users and which users are querying them. And so in order to do that, we wanted to implement something called private information retrieval, which is a protocol that during an exchange between a client and server obfuscates which item in the server's database is queried by the client. So the server does not know and is completely blind as to what exactly was queried. This creates the level of privacy that we're looking for. However, we have to consider a couple questions with this, and it's how inefficient is this protocol? I mean, there's going to be some trade-offs. If we're trying to preserve privacy, is it going to create a really inefficient protocol with large query sizes? At which endpoints within that scheme that I just talked about should we use this protocol? And then how much and if what privacy guarantees does it provide as a whole? Another thing that I did was essentially write a program that simulated how the server would look and the different endpoints where the databases would be storing the key IDs and public keys and the location reports and the report IDs, and tested it on my computer to ensure that it would function correctly and made sense. I also wrote programs to measure timing because we wanted to also investigate, is switching to quantum secure encryption algorithms going to make it inefficient in that manner as well? Not looking at PIR, private information retrieval, but just these algorithms themselves, because they're on based on different hard problems, is it going to make it a little bit more inefficient overall to implement them? So I wrote programs that tested the current encryption algorithms and the future quantum safe encryption algorithms and compared the timing of both. So getting into the results of the method. First, for private information retrieval, we wanted to see the efficiency, like I talked about. So we ran the private information retrieval protocol against a server of varying sizes, or a server with a database of varying sizes, ranging from about 1 million entries to about 10 million. And so that's going to be the x-axis. For the client time, we're seeing really not that much of a change over the course of the increasing size of the database, and that's because it is independent. The client is going to just generate this request regardless of how long or how large the database is. The server time, however, looks more linear in terms of its progression as we increase the size of the database. It's going to take more work on the server side in order to implement this as we make the database bigger. And something to really note here is, in actuality, a company like Apple that has hundreds of millions of these devices distributed throughout society is going to have an extremely large database, so much more than 10 million. We didn't have the computing power to really scale that up that high, but Apple will, and they'll be able to test that. And then the other takeaway is outlined on the bottom, but the majority of the overhead in terms of the efficiency and the timing is going to be on the server side. And you might be wondering, why is that important? Well, we don't want the random users to have to basically deal with all this overhead on their devices. Like they did not sign up for that. It's more on Apple to deal with it. And the good thing about this is that Apple, in terms of its scale, its resources, both monetary and technologically, they have the capabilities to handle this overhead, minimize it, and essentially make it more easily used in this protocol. Like I talked about, we had tests to measure the overall timing and the computational overhead for both the Crystal's Kyber, like I talked about, the current or the future quantum safe encryption algorithm, and ECDH, which is elliptic curve Diffie-Hellman. That is the current non-quantum safe algorithm. For ECDH, I wrote a program, like I said, that tested it. And for Crystal's Kyber, we downloaded the library, built the algorithm, and ran a preloaded binary that tested the speed of Crystal's Kyber. And another thing to note with these is that both of these encryption algorithms have to be supplemented with what's called a block cipher, because they don't functionally encrypt the message. They encapsulate, in terms of the Crystal's Kyber, they encapsulate the message that then can be encrypted with a block cipher. And ECDH generates the key, exchanges the key, and then is supplemented with the block cipher to create the encrypted message. And so what we saw in this result is actually that the computational overhead for Crystal's Kyber is not much more than ECDH in terms of encryption and decryption, and it's actually a lot faster in terms of the key generation, and that's because ECDH involves an exchange between two people of the key to verify that you have the same one, because the whole point is that this key is generated and you both have it, and so you got to verify that it's correct. Crystal's Kyber doesn't work the same way, and it actually is just going to essentially just generate the key really quickly, and so it is actually faster in terms of the key generation. And also just want to point out it's microseconds, which is the unit, so it is really fast overall, and the ECDH key generation is going to be milliseconds. So some conclusions that we reached based off of the results and the tests that we ran for method 1. I've already said it a couple times, but I want to drive this point home that it's not going to be a viable option for implementation, because if we think about the best case, 4 months of battery life and 2 minutes for complete reception, a functional, normal Apple user for AirTags like myself is not going to be near these bystander devices for the amount of time required to pick up the entire key. It's a passing by scenario. You want to just walk by and pick it up. We also measured that it's about a 14-foot max distance required for reception. So as we increased the distance from the broadcasting Bluetooth tracking device, we were consistently picking up about the same percentage of advertisements until you reach about 14 feet, complete drop off, and it stops picking them up. So now you got to put that in perspective and say you got to be within 14 feet, and you have these extra 2 minutes requirements to pick up the entire key. And so it's not ideal for complete functionality, but it could be usable in specific scenarios like research purposes or other things. But overall, Apple's not going to want to introduce this as an implementation. So that leads me to method 2, and it's a promising path. The implementation of PIR is not actually too inefficient for a usable implementation for this encryption scheme. And like I said, the overhead is majority on the server. It's on Apple. So it's not going to cost the bystander, the user, too much energy, too much data on their devices. And that is really good, essentially. And for the second point, for when I measure the timing, Crystal's Kyber is, like I said, not that much slower than ECDH in that it would make it relatively inefficient. It's actually much faster for key generation, and so we're looking at about a comparable amount of time for an end-to-end encryption scheme looking from the current encryption scheme moving to method 2. And so this is an academic prototype that we've created, and it's going to be the best option for both a private and also efficient quantum-safe encryption scheme. But there's going to be future work that's required to essentially actually engineer this in practical use and introduce it to the world. And I also just want to give a quick shout out to all my advisors, Professor Finsky, Professor Mayberry, and Lieutenant Teplov for all their help in this project. And I'm just going to get into any questions if you guys have any.
So you talk about the puck and the battery life you put on the presentation. That is for the specific puck, or is that for an AirTag? What about like an iPhone? How does battery life on that affect it?
Yeah, so the puck uses the same battery with the same voltage as the AirTag, so it functions the same way. We ran into a lot of problems with how to actually measure the battery life, because the way these devices function and their battery is that it maintains a high voltage the entire time, because these devices need that voltage in order to function. It can't just like gradually decline, if that makes sense. So then when we're trying to measure the battery, we're actually getting about like 95% battery for a really long time, and then it just drops off and dies. So it was really hard to kind of measure the battery of this. Instead, so we decided to just let it run until it dies. In terms of a phone, that's going to be different, but again, you don't want to essentially ruin the bystander, the user of this product, or the user of an iPhone's battery life for the sake of this, if that makes sense. Mitch.
In your second method, you talked about moving like a lot of the resource costs over to the server side. What happens if they implement quantum computing in their server side operations instead of conventional computers? How does that affect like the resource resource cost and the time and all those things?
So there's a lot more research that's going to be done in terms of like what can we actually do with these quantum computers. But quantum computers are more about like solving these mathematical problems, and it just happens that our encryption is based off of these problems that it can now solve, which currently cannot. And so the technology is going to increase, and they could get Apple could have a quantum computer in the next 10 years, and maybe that's going to minimize the additional overhead for the server. But it's really, who knows at this point? And it's not necessarily going to be like just making everything run faster, if that makes sense. It just has specific applications for calculations that it can basically perform at a faster rate. Does that make sense? Toya?
Do you plan on telling Apple about your research?
Yeah, so we have a little bit more work to do in terms of this summer we're going to write our paper and submit it for publishing in an academic journal. But before we do that, we are going to send our work to Apple. We're going to let them know our results, our implementations, and our recommendations that they should take into account as we get inch closer to this realization of quantum computers. Are they going to take it and use it? I don't know. It's up to them, and if they decide like the cost-benefit analysis is worth it for them to implement this, like I said, they're going to have more overhead. Do they have the capabilities to decrease that overhead right now, or will they in the future? I also don't know. But they are going to make that decision ultimately, and if they implement it or not, we're going to publish it and hopefully present it at a conference. So thanks, Toya. Seth?
So your second method, you talked about how its effectiveness was largely dependent on timing and distance from this puck. How do you foresee this complicating your algorithm if there's multiple devices within that 14-foot radius that you talked about? And if these devices are going in and out? You said beyond 14 feet, the signal just cut off and those devices are no longer receiving that signal. Do you risk overwriting information by multiple devices not being present for all of the data that needs to be streamed?
Yeah, so first I'll say that the current encryption scheme and the way that it works is the same. It would have the same drop-off at 14 feet. That's just something we measured. It's more device dependent. It's a Bluetooth hardware specification, and just the way the waves propagate. That's independent of the actual algorithms and the implementations. What I will say in terms of oversaturation of the environment, these are broadcasting a lot. And so the environment is going to be oversaturated. However, they have unique identifiers and pieces of information within the payload. Like when I showed you earlier, we can get back to it, right here. So the payload is the highlighted portion down here. In this case, I made it all zeros and then the fragment number, just so I could read it. It was just for ease of use and understanding it. But in actuality, there's certain information in there which distinguishes these devices from each other. There's unique identifiers, there's MAC addresses, there's all of this information which allows the device, which obviously we don't see this part, but it distinguishes them and creates these location reports that it sends to the server separately. So it's not really a problem with mixing up.